So we'll start the conference on this Friday, and the first talk of today is Global Normalization for Centers of Planar Vector Fields by Professor Eduardo Grota Ragazzo. I would like to thank Eduardo for attending the conference.
Thank you very much for the invitation, particularly to Ricardo and Douglas. The conference has been very nice. And well, I will talk about this work, global normalization for centers of planar vector fields. I will directly explain the problem. And just show a picture of our founding fathers here, of all these in Brazil. Maurício Peixoto, Sotomayor, Marco Antônio, Gutierrez. So I like this picture very much, and I like Marco very much. He has been such a great friend, and I learned a lot with him. So anyway, happy birthday, Marco Antônio. Well, the summary of my talk, I will start with this question by Carmen Ciccone, and then I will present 4 theorems that are in this work that I did with former student Francisco do Nascimento, who works in Universidade Federal do Vale do São Francisco in Petrolina, and then I just some slides with related work, then elements of the proof of theorem 1, elements of the proof of theorem 2, and the conclusion. I will put the motivation for me for this kind of questions, open questions and acknowledgements. Well, the question by Carmen Ciccone was the following: if differential equations, second order differential equation, system of 2 first order differential equations has a center at the origin, surrounded by a region consisting of periodic orbits. When is there a change of coordinates defined on R such that in the new coordinates the differential equation is Hamiltonian? So we answered this question in this paper. Essential, right? Not in the analytic, real analytic. When I say analytic in this talk, I always mean real analytic function. So now I will present the 4 theorems that is in this paper. I will discuss some of them. The first one is a local version of this theorem. So it's a positive answer. So for this theorem locally. So suppose the real analytic vector field is of this form. So I will just write it here because I will. Yeah, I should also. I will have 4. Okay, here, right? So I have this planar vector field here, and the orbits are. You have a center, non-degenerated center. Then you have a foliation by periodic orbits. Everything is analytic. So this is the first one. I will skip one here. And then I will put another one. This another vector field, that's this one. So I say I can transform one to another. So essentially, we can describe the solutions of this system using displaying the function v. So function v is something like that. These orbits essentially are related to the level sets of the v. So I have here the phase portraits. Again, something like that. So this is, and moreover here, it's a local version because I'm saying that you have a particular orbit here, gamma, and I do this transformation inside of this. The orientation here is always the orientation in this direction. So I can do the conjugation inside this region because outside I could have other stuff. I could have a saddle point here. So this is the first result, sort of local result. Then there is this global result saying the following: if this foliation goes, so the whole R2 Then there is a change of variable that maps this possibly to an interval. So this p is not defined everywhere, but it's defined in some region. With two asymptotes here. So there is a conjugation between this, the whole plane here to this strip. So essentially, the phase space here is contained between these two A's. This is the y direction, so it goes to the y direction it goes indefinitely, but in the x direction it has these two asymptotes. And so this is the second theorem, and essentially I'll give the elements of the proof of this one, not of the first one, because the first one is easier. Well, it's a consequence of this one. In between, I need to do the proof another essentially normal form. There was a local version for this theorem. Well, we think we proved the global result. I hope it's correct, but anyway, we'll explain it. I checked it many times, and I think it's a natural result. But anyway, you always should be careful with this problem. So, what's this intermediate step? You take and you do a circularization of the orbits, transform them to circular orbits, and the orientation is probably incorrect. Definitely it is incorrect. So the signs here, yes, the signs, these orientations I think doesn't match the sign, but it's a minor problem. Anyway, but here, what do you have here? The difference here is that all orbits are circular. And the vector field, I don't know which letters are used for this vector field, K and P. And the omega appears in the, yes, here, yes, omega. Let me put omega R, P, omega R minus Q, I think that's correct. And then, and I'm sorry, here it's R. And R square, in this case, is R is square. And there is a 2, right? Yes, there is a 2. Yes. So that's the, and this is what they call global Poincaré form. This is the global Poincaré. Because Poincaré had proved the local version. So you have a non-degenerate center, and then you have a foliation around the periodic orbits. So you can do this, right? So just an extension to R2. So let's see now. The fourth theorem. The fourth theorem I will not prove because it's essentially my previous paper on the subject from 2012, publishing this in the qualitative theory of dynamical systems, and it's the for it was the motivation for all this. Because suppose you have a second order differential equation that's even with the velocity. So this is the vector field. Now assume it's analytic. Moreover, this is a strong hypothesis. You have this vector field, right? The other vector field, where I replace this v squared by this letter z. So also, this is also a second order, it's a planar vector field, but it's trivial in the first component. So it's a first order OD essentially. And I assume that the flow of this OD is complete. So in other words, all solutions can be projected, in fact, to the U variable. So you have the hypothesis here is that all solutions of the system project. I think here is impossible to see, but it's easy. you have U and Z, and all solutions project to the U variable. So the U is the time in this case. So if this hypothesis is true, then there's a change of variables that modify this vector field, the original one, to this one. But you see, it's more or less like this one, the mechanical normal form, but there is this factor, this positive factor, so you have a time reparameterization of the orbits. And in this theorem, in this paper, I try to remove this. And it's a long paper with some mistakes that I think they are all correctable. So this paper that I'm talking about, this second theorem in this paper, is a sort of first correction to this paper. And then we decided, here's everything is C infinity. We decided to do the analytic case to be some related works, but there are so much work for planar ODs that's absolutely impossible to keep track of everything. So anyway, but at least during what we look at why we were working this problem were these periods, these papers for proposed interpolable systems by Libre Valls, Teixeira and Young, non-degenerate centers and reversibility, degenerate centers and reversibility by Guilherme Maza, degenerate centers analytic integrability, which is a delicate problem for Chavaniga and collaborators. Then isochronous centers, the period function and its relation to partial differential equations. This is a very nice book by Renat Schaff. And variation of the period function by Torregrossa, Sanchez and Sanchez. Well, elements of the proof of theorem 3. So here I think are the main ingredients we used in this proof. I will not do any proof in detail because they are long. This one is not so long. Oh, they are not so long, but they are very technical. Anyway, but T of UV is so in other words, we start with this. So this first result says the following. You take a point UV on the plane and you define the function T that depends on U and V. And this function is as an analytic function U and V. And this is a consequence at the origin of the term by Poincaré, because it's not obvious at the origin. It's also discussed in this paper by Villani. This function is globally analytic. And then I need another function that's the area, because the idea here is to mimic more or less the proof of the action angle variables that we do in Hamiltonian systems. So I need that the area function be also real analytic, and also this also we took, you see that the data is analytic when you compute the area function. And so I is also analytic. So since you have this, now you have these two functions, the period function as a function of U and V, because the period function need to appear here several times. And I use this period function as a function of different variables. So you can write it, as you're going to see, in a different way. So this first step is a function of the point on the plane. And then we have this function, the area function, and then we take the gradient of the area function with respect to the usual Euclidean metric, and consider this vector field. Why I need that? Because I want to construct a global transversal to this, foliation. And then I need, but the point is, there is the question of this curve. If you start with the point here, you have an analytic gradient vector field, you get this. But there's a problem with the origin. So you have to cross the origin with an analytic curve, sort of invariant curve that goes through the origin. If it were a saddle point, it would be an unstable manifold, for instance. But then we use this result by Musu, that there's just regular analytic curves through the origin. This paper by Musu is much more general than we use here. It's a very simple version. But anyway, through the origin says that each open half branch of the curve is a gradient trajectory. So So there is an analytic curve here, such that going through the origin, such that each, of course, this is at rest, right? But then each half of this curve is an analytic curve. So you just continue this inverted curve up to infinity, both directions. After doing that, we have this. This curve here. Then I'm giving the elements of this theorem. So we have to construct another analytic curve here. And that is, well, and then we do this, it's not if I give you the details here, I cannot even give you the details now here. But anyway, there are lots of details and computations, but you construct this other analytic curve, but it's natural, right? You cannot take just a straight line. Why? Because in some sense, the time it takes for this solution to come from this part of the curve, each circle here, each orbit, crosses this curve that they call beta, right? This is the beta curve, to 2 points. And the time it takes to go from this point to this point has to be the same time it takes to go from this point to this point. This is the reason that you just must be careful to construct the other curve, but it's doable. And after you construct, and then you do the obvious thing. You cut. You see, there is two lines here. You see, this is a full line and this is a dotted line. Full line and dotted line. Why? Because you construct the conjugation first in two charts. You eliminate this one, so you start with initial conditions which are not on this line. Then you move the point here, you move the point to here, then map it to the other point, and then comes back here, and then you define a function that comes from this point to this point. You don't consider any point on this curve, and then you do the conjugation, this open set, that misses the origin and this dotted line. Then you do a second construction that you miss the origin, the dotted line. So you have two charts, conjugation of two charts, and then there is a third step where we prove that all these two, the conjugations, they are analytic and they coincide in this open set that does not contain this line, this line, and also the origin. So they coincide in this region. So at the end, they coincide in all the annulus without the origin. So the origin is still out of this. So the conjugation, using these two charts, it does the job except for the origin. So still, you have to prove the analyticity of the origin. Analyticity of the origin, how did you prove? We proved using the Poincaré local theorem, but it gives also some work, because generally, if you do the normalization with Poincaré, you get a diffeomorphism, a local diffeomorphism, analytic diffeomorphism from here to here, that does not coincide with this one that we constructed. It usually does not coincide. But then what you have to do, the Poincaré normal form, it's invariant by two transformations. One is dilations, that we use in another step of the proof, because it's more or less obvious that invariant by dilations. Why? Because you see you have circles here. So a dilation takes circles to circles. So any map that analytic map that takes circles to circles, we will leave this normal form invariant. The second one is the following. You can rotate each circle by a different angle, in fact, and the rotations also preserve the circle. So you have an analytic rotation that differentially rotate each circle. You also preserve the Poincaré normal form. And then it proves the following. If we do dilations and rotations in a correct way, we show that there is a Poincaré normal form. There is one such that coincides outside the origin with ours. So if coincide, both are analytic and they coincide in an open set, they also coincide at the origin, and it shows that our map, our diffeomorphism is indeed an analytic diffeomorphism from and a conjugation from this part to this part, and this proves the first part, the global Poincaré theorem. So these are the elements of the proof of the first theorem. Not the theorem, the third theorem. That's the conjugation between the original flow and the global Poincaré normal flow. Well, now we go to the proof of the second theorem. The second theorem is the global one. As I said, the first theorem is just the local version, but it's contained in this proof. The proof on R2 is trickier. In fact, I thought it would not be true, but at the end, the only thing I will prove is a proposition originally by Poincaré, but the proof is not. I think it's let's save this. Anyway, but now what we have to do? This is the Poincaré normal form. We first transform it. We also have an intermediate step that I will not write there because there's no space. But anyway, you see, you have this vector field where this function, the period function, essentially, this is the frequency function, right? Not the period, but the inverse of the period is here. And then we have to find another vector field that has essentially the vector field. The direction of the vector field is the same, but this area form, or this factor, depends not on the radius, as here, but depends only on this variable, on the Q variable, the horizontal variable. So you have to do this change. Well, let's just go to the end of the proof, then I come back to this part. It's in blue because, of course, this is the point. After we prove this, and this is the point of the proof, we define a new variable, it's an easy part. We define a new variable x, and after some computation, you see that you can transform this one in an easy way to this one. That's exactly what we need. So essentially, this is the easy part. After we do this, this is the easy part. So the point is you have to change this area factor from here to here. And this, of course, this is important, has to be positive. Psi has to be positive, cannot be zero. So this is positive, because it's the frequency, and this has to be positive. This is also a difficulty in this construction. Anyway, so what do you do? So the transition from the vector field Poincaré normal form to this other one. Well, this is the period function written in a different way now. Essentially, you have this R squared is the same R that we had here, there. So you have this, and then it's the following. Then we have to find this psi. I'm not describing the way we find it, but it's essentially this. It leads to the Abel equation. This is a very standard thing that appears in this problem. When you give the period and you want to find the potential. You give the period, you want to find the potential. So it's a Abel equation. And moreover, maybe there is another way to prove this anyway, because a point is you have to control the solution of Abel's equation. It's easy to solve the Abel equation, very easy. Abel solved it. What it's not easy is to prove that after you solve, let me write. So this is a solution not in the usual way. This is the way I took from the paper by the book by Schaff. So you have to make change of variables in usual. Here it usually appears as square root of something in the Abel solution of the equation. And here just do a change of variable and transform this square root in the denominator to this nicer expression. So where tau is the original, period function, and psi is the function I want to determine. So essentially, I have a formula for the function. Everything is analytic. Essentially, you see, if you look this field, no problem. The problem is the following. And in fact, if the period is an increasing function of r, if the period increases monotonically, the proof is finished. Why? Because the point is, this is positive, this is positive, this range, and this is positive. So this is positive, and that's it. You're done. The difficult part is the following. If the period function is no increase, it can be strictly decreasing, it can oscillate. And then what happens? If this is negative, you must be sure that this is positive. And this is the difficult part of this paper and the 2012 paper, is the positivity of the solution of the Abel equation. This is the definitely hard part. Anyway, but then, so how do we handle this, the no increasing period? So one has to, again, what I do the formula. I displace, because if you see this period function, you can move this radially. So you can transform the period function using an analytic diffeomorphism. And this gives you a hint how to do to handle the problem, because then you reparameterize the period function put here with the hope that you get a positive expression for some parameterization. And this is what we do. We get an ODE for B, but this ODE has to be that we can solve, because a linear ODE, you solve it, variation of course this formula, but then you have to, the solution has to have some properties. I will not describe these properties because it's a lot of time, but at the end, and here I thought it would not work until I found this paper. What happens here? This tau prime can oscillate a lot. So in fact, this tau prime can be negative. It can do with my hand. So this period function, it can increase and then it decrease and then increase again, then decrease again. And as it increases and drops out, this tau prime can become very negative. Very, very negative at certain points. Because you can make it increase a lot and you can do it analytically. And then it decreases dramatically. So you said, well, little hope that we can do is positive. Because when it increases dramatically, if you take a delta function decrease instead, you make it negative. So it will be very difficult. But then I realized that if we can find this, then comes the question. Suppose I give you any function that increases as fast as you want. Positive function, increasing function. Imagine a function that increases e to the e to the e to the e to the e to the, and then put something else. But it's defining the whole x. Is there an analytic function that increases faster than it? And the answer is yes. And maybe for some of you is an easy result, but for me, it was a big surprise. And again was for Carré. And then I found this proof by Lepson. It's a note by Lepson on this theorem that it's so clear that I decided to at least prove something in this. And this probably is correct because it's not my proof. It's an adaptation because I need to be honest. It's an adaptation of the proof in Lepson. Anyway, but there is a proposition. So I think MR is the soup of this derivative of the period function in this from 0 to R. So this is an increasing positive function. So the claim is there is an entire function, M of Z, entire function, with no negative coefficient, such that this entire function, restricted to positive R, of course, is larger than this function. That's greater than this because essentially this function by definition is greater than this for all R. And moreover, it's odd. So we start proof. Since this tau 0 equals 0, and for some reason, and tau prime is analytic, there exists a constant C such that this is MR is less than 0. So in the beginning, you just bound it by and moreover, close to the origin, you control everything because the point is as it goes away from R large. Anyway, but then how do you construct the function? Then you consider this. You define the sequence of numbers. It's amazing. So you take the integer. Here I take all the integers. Every positive integer. I construct a sequence increase of positive odd integers. So all these lambda k are odd integers. But they are such that for any k, lambda k is so big that and it it's larger than m of k plus 2. M is this function that we need to bound from the loop. So this lambda k clearly exists, but increases very fast, this increases fast. Then you define this function. M of z is this, times the sum lambda k is those numbers, and z over k. Well, the first thing that happened, if I does this converge? This is an entire function. Why? Because you fix z. So if you fix z, at a certain point k is so large, that's larger than z, right in this side. And then this is larger than 1. Then you have this sequence of increasing odd numbers, and you can use, in fact, the geometric series to bound this series. So in fact, it's an entire function. Moreover, now you have to show that it does the job. So you take this function, so all terms are positive, because r here is, we are restricting z to r greater than 0, positive real line. So mr so each term is positive, so you just take the first term, only this term, lambda j, so this is greater than only this term, r over j lambda j, which is less than j plus 1 pi, because r is greater than this, we are in this equal. And then it's greater than this because, let me see, because j plus 1 and j plus, because of the choice that we did. This is the trick. And this is greater than this because this is an increasing function. Here the origin, this is true, is not so difficult to show. Then the proposition is proven. And then we use this function, this m of z, put in the ODE, solve the ODE, and essentially prove the result. I'm going fast, so I'll give the one. But I have some comments on this, some comments on this. So let's solve it. The 3 terms are this, the 4 terms are just give an element of the proof of the 2 of them. So, and then I will talk about the conclusion, my motivation for this. The motivations for this paper were 2012. The paper, I think, that's the paper that gave me a lot of headache. All my career, that by far this is the one that, although it seems to be a simple problem, gave me a tremendous headache because it was difficult. But it came from this question. This Carlos Rocha works at in Lisbon, at IST, and then he has in a talk, but also in this paper, this question: when the global attractor is global attractor of this PD, this parabolic PD. It's a very nice result, in fact. This parabolic PD. When the global attractor is more snail, in other words, all critical points here are saddle points, and the manifold, the invariant manifolds intersect transversely. There is just a smooth homotopy from one equation to another that reduces this to an equation where this, another equation where this is, or f1 is even function of the second variable. And to understand this periodic, this critical points of this equation, you must understand the solutions of the ODE. So, in particular, the period function. So he asked me if it were possible to do this transformation. Then I started working on this, and I spent 2 years working on this problem. But that was the origin of this. So it has some relevance, this terms in this field of parabolic peaks. Wow. Shikori does not put the question, restrict the question to a non-degenerate center. It's put it in general. If the center is degenerate, I don't know. Really, I don't know. It's much more complicated problem. Because non-degenerate center, in fact, you have infinitely many types of non-degenerate center. So it's definitely, maybe, doesn't have a definite answer, maybe. Because the degenerate center can be so complicated locally that I don't know. Is it possible to analytically transform the vector field? This one. That's in my previous paper. To this one, when XIII has not only a center, but also finitely many non-degenerate centers, etc. So this is a complicated problem. Why? Because instead of having this, I'm asking, if you have this figure, center here, you have a saddle here, etc. Can you transform to something like this? As I said, my previous theorem has some problems in the proof, the local part that I think I can correct, but I will not. Right? Because I got so exhausted with this problem that, in fact, sometime I think I wanted to forget this paper. Something that happened to me. I work, see, if I have a colleague, as a student, who's a very nice guy, then I can talk about this paper, we can join talk. But to sit myself as I did 2 years, almost day and night, in these warm holes, I by myself or not. Anyway, but why this question is interesting? Because let's see. Because one thing that we may ask is why do we want to prove some kind of theory? You see here, I have a vector field with 2 variables, P and Q. When I go from here to here, essentially, I realize in the case of the center, not in this case of this, that the invariant, the analytic invariant of this problem, what really matters in this problem is the period function. And moreover, not only the period function, because the period function can also reparameterize, etc. But what is really important are the critical points of the period function, so the maximum and minimum of the period function, and the critical values. What are the values? Because, so you see, this function omega r encodes essentially all the information in this case when you have a single center. And then when you go from this to this, you think you do not gain much. Why? Because here you have the period function, here you have even a more complicated thing. You have a potential function that is, again, easy to visualize the flow, but to get the periods of the solutions, you have to do an integral. So in other words, you think, from here to here, why do you do this? This is more interesting than this. And maybe it's correct. But you cannot pass from this to this if you have a saddle point. No way. You bump into here. But you can go from here to here, even if you have a saddle point. So again, you encode all the information on the field here. Of course, you must have hypothesis here, because even in my theorem, this theorem that I showed you, it's here. For this vector field, I have a strong hypothesis that the other vector field is, if you put 1 instead of v here, you put z here, so you have this essentially one-dimensional v, the solution has to be globally defined. There is a result, I worked it out many years ago. You can break into several parts because you have several regions that you can break the flow where you have global transversals, because you need global transversals. So, and then prove us another version of this, but this, I think it's more complicated. So, of course, you need some hypothesis on this P and Q. But anyway, but I just want to point out that the passage from a vector field of this form to this one, when possible, is empty, because you encode every information of these functions only on this one, in the critical points of this function v, because the critical points of v become the critical points of this one, and also, so I think the question is relevant. So these are the open questions. And finally, acknowledgement, right? I think the most important part. I acknowledge very much Professor Antonio, in fact, not only for, because I talked to him, he remembers about this paper. And also, he has also a related paper when he used, in fact, I could not find in my file this paper. You use discontinuous systems to work out this. Remember, a very nice trick also related to this question. It's not exactly what I asked, but it's related. But we talked a lot about this. Professor Marco Antonio helped me a lot about my life, my career, as we are a great friend. We've been in conference together, talked at lunch. We also cheer for the same Brazilian team for years. The best of the world, of course. And also, Jorge Sotomayor, who is also a great friend, also helped me a lot with this paper, taught me a lot to me. Carlos Rocha, of course, because he gave me the problem. Bernard Filler, he also discussed the results. And Jamal Libre, because the first paper, it was here in Brazil, and he was very important. In fact, I talked to him, and in fact, it was submitted to the journal because he suggested to submit to the quantitative theory. And moreover, it's very difficult to publish a paper with 150 pages. So, very difficult. And then the guy said, well, cut the details. But you know, I had cut a lot of details in this 150 pages. It was wrong. I'm not saying the result is wrong. The reason that because for instance, if this is correct, what I'm saying now, and I'm being cautious because it is part of the other one. The problem, the statement is also correct. I quite believe that the statement of that paper is correct, but it had to be fixed in several parts. But of course, I think that it's correct. Maybe it's not. As always, there's a chance until you really write a correct definite proof that people accept this. Anyway, thank you, João-Maria e Carlos Rocha, por essa ótima oportunidade.
Thank you, Godoldo. Questions or comments? I have a question. What happens if you consider the initial systems as a Hamiltonian systems and you consider the Birkhoff normal form of the system?
Yes.
It simplifies the proof and
This is exactly, well, you can say the Poincaré normal form or Birkhoff normal, because the same. Here, I think maybe I use because Birkhoff normal form, I think it starts with the Hamiltonian system, right? But you see, this is Hamiltonian. What I'm showing here, this is Hamiltonian. To be Hamiltonian, in fact, on the plane is not so difficult, because if it preserves some area form, it's Hamiltonian. So essentially, image is the same. So here is a global, sort of global normal forms. For Hamiltonian systems, I saw, in fact, modern proof of global action rule variables. Maybe this theorem is known, because for me it's a natural theorem. I did not find it, at least in the way I'm using here. But your question is essentially maybe you're right, because you can use, you can write this, rewrite this proof using Birkhoff normal form, but it has to be a global version. And then, moreover, maybe not, you know, I'm going to think about, I don't know.
more questions or comments?
Nice talk, Rodolfo. Thank you. I may have lost something, but the hypotheses you're assuming on P and Q are avoiding the isochronous centers.
No.
No. T, the period function could be constant because you are using that to construct the change.
Well, isochronous is a big problem, right? I'm not avoiding isochronous. What happens? T is a constant function, right? Constant function, in fact, is not so difficult. The problem is to know when the second is isochronous. Suppose you know the second is isochronous, and then it works. So I think don't use it. The problem is, a big question is to know when the second is isochronous. Because here, you see, I'm using two things. First, well, this is in the question by Ciccone, in fact. So you have a non-degenerated singularity, and you have the foliation by periodic elements, which is analytic. So I'm not using that as
because you were using the period function to construct a change of variables.
Yes, but you see,
it wouldn't be a problem if it's constant.
No, let me tell you what happens. Suppose it's isochronous. What happens? You see, the construction depends on these times. In fact, of course, you have to compute the time because this function, this first arc you construct using this gradient vector field, and if the foliation here is not so good, of course, this line will go around and you don't know how. So essentially, you have to. The only thing that even because this is the reason that the isochronous center is a problem. It's a global problem, right? The problem is you have a time. The time it goes to go around is constant along these orbits, right? So here, you have to do computation, so I don't see any difficulty. Moreover, at the end, you see what happened. Let's see. We linearize in the case of isotropes. Let me just check because I don't know. But let's see this another point. Let's dedicate this one. Isochrones, this is 0. So again, this is constant. So what you get? You have to integrate the integral of sign, then you have to transform it. I don't know. You get psi. Well, let's see. Psi is constant. And you get harmonic oscillator. Exactly, you get harmonic oscillator. Psi is constant and harmonic oscillator.
Okay, thank you.
So let's take the speaker again.
Tem que ser uma restrição dos bichos, como é o caso da dimensão 1 e mais, ela tem que cortar todas as horas duas vezes. Talvez parece hipótese, parece que todos os pontos que estão nessa linha. Aliás, pode ser. Mas ela parabéns. Eu vou mandar para você. Eu vou mandar para você.
Let's continue. It's a pleasure to introduce the next speaker, Professor Yaramambi from the Union College. And he's talking to us about bifurcations in random mechanical systems.
Okay. Well, thanks very much, everyone, for being here on the last day of this long week. And thanks in particular, of course, Marco Antonio. I will speak about bifurcations of random dynamical systems. As most people in this audience probably rarely have looked at random dynamical systems, I'd like to use the opportunity here to make some kind of propaganda for this field, try to explain that there's things to be done, and that maybe some of you can do this. So first I'd like to say something about Marco Antonio and myself. So there's some issue that I have, is that I feel quite Brazilian, and I also feel quite connected to Unicamp, even though the facts point to the way that this is not so obvious. But at least I met Marco Antonio first time in 1993. I was still doing my PhD, and I remember sitting on a little table on the side of the beach in Cargés, and Marco Antonio explained to me how to do bifurcation theory of reversible systems using contact singularities. That was very interesting. It was also important. Then I found a mistake in my own PhD thesis. So that's always useful. The first time I came to Unicamp was in 1999, now 25 years ago. That's a shock. I apologize for that. But I have been coming to Unicamp a lot. I was a visiting professor in 2010. When my son was born here. I was also in Ciências Sem Fronteira. And last but not least, Ricardo was so kind to send me Teos Monsanto to do a PhD with us. But I feel very connected, and I would say that I hope that this connection will continue for as long as I'm around. I'm very excited about things. I must also admit that I got lots of ideas from Marco Antonio. I love the geometric approach. There's always a picture. I remember Marco saying, anything that can be drawn exists in some sense, and I think that's a very nice starting point. I would also like to say something about Paulo Rufino and Pedro Gadorno. Many ideas that I had made me start working on random dynamical systems actually also came from them, even though I don't have any paper with them. I would like to maybe say also for funding bodies, research is not only writing papers, it's also a culture of talking to each other and getting ideas from each other. Okay, good. Marco Antonio, muito obrigado para tudo e muito parabéns. Okay. Okay, good. So I'm trying to say too much in this talk, so I'll try to say something quickly. But because many people know these things. So dynamical systems, I would like to just kind of sketch what I think dynamical system theory has been doing. We try to kind of understand qualitative theory of differential equations, of dynamical systems, maybe not of differential equations. And there's some pillars of this, I would say. One is bifurcation theory. We want to understand, do we have qualitatively different behavior in different regimes of our models? So if you change parameters, for instance, we get different behaviors. But we found that some of these behaviors are kind of complicated. And then there's a trick. You say, well, I don't really describe all the dynamics, I'm just going in some kind of probabilistic setting. And this is nice. So sometimes the probabilistic setting is so that you have very nice answers, like you have a chaotic oscillator. You cannot predict where it is, but you can actually very nicely predict that in a certain part of the state space, it will arise with a certain frequency. So you get probabilistic theory of dynamical systems. And of course, we have this whole issue about chaos and how to understand intrinsic limits to predictability, which of course is philosophical important. Okay, so people have done lots of things with that, motivated by phase transition theory, trying to understand the basics of statistical mechanics, which is one of the many groundbreaking things with the physics, and also other practical things. Good. So, while this theory of dynamical systems is great, it also has some limitations. And I remember a Trieste meeting in 1995, where Jacopoulos looked into the audience in the opening speech. He says, like 10 years ago, 50% of the audience was physicists, and already in 1995, the physicists were not there anymore. That was an issue to him. And I think it is an issue also today, that in some sense dynamical systems is not generally, or not as generally kind of found interesting by people in applications as they should, because we see dynamical systems everywhere, but they don't see our dynamical systems everywhere. So one of the reasons why I started looking at systems with noise is that I get people banging on my door and saying, oh, I have some interesting question. It must be a bifurcation question because I see something changes, and they come with some models, and these models are not models that I used to. They're models that invariably have some noise because they like noise, and all kind of applications looks more realistic. Yeah. So what kind of applications do we have? Like, well, for instance, geophysical fluids, climate, weather, turbulence, life sciences, hydrodynamics, neural systems, opinion dynamics. Yeah, you just name it. There's a whole plethora of interesting areas where, of course, there have been attempts also to do these things with PDEs and ODEs. But there's a certain kind of like engineering reality that if you have a nice solution curve, and in the data that they have in the lab, it looks all like jagged. They say like, look, it's kind of nice, but it's not what I'm looking at in the lab somehow. So that it could, of course, be that what they're looking at essentially is that, but there is a certain kind of like understanding that they're interested whether or not these fluctuations that we see, and so are they really important? Are they important to make the models more realistic, just to look realistic, or are they new phenomena? Are they new phenomena due to these fluctuations? Okay. So there's several motivations for noise that drive me. One of them is that people knock on my door and ask me questions that I can't answer. That's been my overall drive. That's probably why I'm here in the first instance. But if you think a little bit about it, you can think of sort of the simple setting is that you think that there's a system which is just driven by some signal, you don't know the signal. First you have power lines, and you know that the energy is not generated in a constant way, so you get some fluctuations, and And you can think of this as a noise. Yeah, I'll talk later about what I mean by noise. But that's other motivation. For instance, we have high-dimensional systems where we like to describe the behavior as a low-dimensional system where a lot of degrees of freedom are so basically not averaged out, but is taken as some kind of background fluctuation. So maybe sometimes we have high-dimensional systems say, in a network, and that's some degree, many degrees of freedom we don't want to describe, and we hope that it just contributes in some kind of like systematic way as a noise, and then we can concentrate on low degrees of freedom and understand that as well. Another one is not so often used, but I think it's a good one. So one problem with dynamical systems is that we know that we have equations and we cannot solve most equations. We cannot solve. We cannot even understand qualitatively what happens. We must make sure they're not too degenerate. So there's a whole topological theory on that, but that also has its problems somehow. So with many of these problems, we cannot really find a good set for which are kind of like outside bifurcations, for instance, homoplane tendencies or something that you get very complicated dynamics. So another way is to think about, well, if you don't know the equation of motion, why not we let them fluctuate a little bit? So anything that should be true for models that we don't know what the equations are, that should probably also be true for something that fluctuates. And then you can use these fluctuations in the equation of motion to maybe control better the behavior and get rid of like esoteric and strange behaviors that are only true for very special models. So it's a different way to look at generic dynamics. Okay. Good. Well, okay, maybe this is here not necessary. We know that the bifurcation theory people here call bifurcation theory, so I will skip this. We know that you can do singularity theory. So here's the kind of systems I'd like to look at. Two very simple types of systems. One is some kind of like, say, diffeomorphism or endomorphism with some noise. I'm going to make it simple as possible. I'm just going to iterate some mapping, and every time I iterate, I just perturb it by some vector where this psi will be taken randomly in some sense. The sigma is just the amplitude. So what I do is I'm going to iterate in a sloppy way. Every time that I iterate, I say there's a mistake in the iterate. And this is very similar to something that looks much more scary. Here's an SDE, stochastic differential equation. That people look to think that this is some kind of like linear process of only motion. Differential equation, a continuous time version of something that looks pretty much like this, maybe not with this bounded noise, maybe with some Gaussian or something. So what's important here is that if we add some noise in order to get some good mathematics going, we need to have some conditions on the type of noise, and here it's taken to be some kind of diffusive, and diffusive noise is nice noise, and the diffusive noise you can do things that otherwise you can't. If you do general crazy noise, then of course the world becomes crazy. So I think it's not a good idea to not start to make it harder than necessary. We want to have good noise, and good noise will help us to understand dynamics. Good. So now there's certain settings. So many people that study noise in dynamical systems study a sort of small noise limit. And as a caricature, what happens in small noise is that basically everywhere the noise doesn't make any difference, but if you have saddle connections, and so you can now jump saddle connections with the noise, and actually close to kind of saddle points and hyperbolic points, you get basically also a back process, so you get some kind of Gaussian that comes into. But actually most of the dynamics is just flow box in the right direction. Small noise doesn't do that much, but around singularities and connections you have to be a bit careful. So a lot of people do this kind of stuff, but of course often noise is not small. And another problem is that for these small noise assumptions, it has to be locally small as necessary for things to make it easy. And the problem is we know in dynamics that we have lots of dynamics that is on very fine scale, so we can't really find the smallest scale to which we can. And there's a problem with the small noise assumption that some things cannot be done by small noise. And then of course there's large noise. If there's super large noise, that's just noise, so don't need to worry. And any underlying dynamics is just not interesting. The interesting part is where we have the noise competes in some sense with our deterministic equation, and then we get things like we call, noise-induced phenomena. You get something where the noise, some kind of like, is going to do something which maybe is very different from the deterministic system. So I'm not thinking of perturbing, a deterministic system with some noise. That's more or less a small noise assumption. I just want finite size noise that means at some scale, somewhere, it's going to make a difference. Okay, so what is the system with noise? I said already, we think of it as something that's driven. So driven systems are basically non-autonomous systems. A system where over time the equation of motion change, and he is changing by the input signal, and that's what we call the skew product. And so that's the underlying basis. So we can think, for instance, of something that drives something. For instance, in the setting that I just described, with this mapping with the noise, that we give a sequence of what I call perturbations of noise realizations. This psi is in some delta. Give a whole sequence, and then what we do, we iterate, and every time we iterate, I just read from the sequence which perturbation we're going to take. Then I have a dynamical system that lives on the state space here, but also on this space of realizations of my perturbations. So I can think of this as a non-autonomous equation, where this describes basically some kind of the time or something, make it non-autonomous. Okay. So the problem is with non-autonomous dynamics, people don't understand this very well. Because, yeah, if you don't know what the equation of motion are doing, what can you say about something? Yeah. So, in particular, you can have very crazy behavior or strange behavior depending on how you choose this driving. So that's a hard problem, so people are a bit stuck doing non-autonomous dynamics. But it's a very important problem because everything we find almost interesting in the world in dynamics is non-autonomous dynamics somehow. So because you drive a car, you look at the weather, the earth changes and stuff like that. It's not autonomous, and definitely we cannot so easily take time to infinity either. Good. So when do I call this non-autonomous systems now something that's random or not with noise? Is when I put some statistical property on this noise driving. So I said, like, look, for instance, it's kind of the shift map that I just wrote down is maybe it has an ergodic invariant measure, and that describes me some kind of like good statistics. And now think of that I don't know the driving signal precisely, but I know some statistical. That's the trick. And so how can we then use probability theory? Well, by ergodic theory, we now know we can basically make statements that leave out kind of like some kind of zero measure, say, of noise realization. That makes our life a lot better. And so we can actually cut down on some really crazy things using the ergodic theory here. So this is nice. So here noise helps us, but this is this kind of assumption. We have the hope that we can make some statements that hold for almost all noise realizations. If that's not possible, maybe we can do high probability. Yeah, so this sidesteps in some sense the general non-autonomous setting. So sometimes when we do random dynamical systems, we learn a lot of things about non-autonomous dynamics, and then we can use the probability theory to help us to make some nicer statements. But there's definitely a communication between. Okay, now look here. So an SDE is also a skew product system. At least you can think of it like that. And you can think of this as an ODE which is driven by some noise. Now, because of the technical assumptions of this SDE, unfortunately, this function that drives the noise now are typically not differentiable at all, and so you have difficulties integrating these things. But apart from that, it's kind of the same idea. Yeah. So also SDEs are just dynamical systems driven by some rough driving, but the driving is such that we can still kind of integrate things. There's some technical issues there. Basically, for the equation I wrote down, when you have additive noise, this holds immediately. So you can just write down how to integrate these equations. Okay. So that's something else. So people in dynamical systems often don't do SDEs. Say, oh yeah, SDE is not mine. But probability theory people don't do dynamics. That's a missed opportunity. So for those of you under 30, have a look around somehow. You can really learn things about SDEs, and I will show you, using dynamical systems ideas. Of course, technically speaking, some people say, oh, an SDE, that's just a generator of some Markov semigroup or something like that. Now, of course, if you think of it like that, then there's no dynamics. But if you think of the SDE as a skew product, as a model of something that's driven by realizations of the reading process, then it's dynamic. So it's also a choice. I prefer the latter choice because I don't know, if you don't have the interpretation, I don't know really what it means to write down an SDE or why you write it down. Anyway. Good. Okay. I say a lot of things. I have to watch some time. So, one thing that's sometimes confusing, and I just mentioned this Markov semigroup, is that when we do SDEs and so, a lot of people say, oh, so we go to theoretic Markov process fine. So Markov process gives you basically, given the state, gives you a probability to go to a different state and such on. And you can involve that. Now the issue is if you do that with SDEs or with a random dynamical system, you can't do that. But you get a theory that basically just gives you a theory of single trajectories. Yeah, I have a point, and then I have the chance to go somewhere else. And that's also where I got a theory of dynamical systems and deterministic setting. But when we do, say, topological theory, we usually don't do like that. We're very interested in how all orbits link together. We are, for instance, in the phase portrait. Phase portrait is not a model that says if I have one initial condition, it goes somewhere. For sure, it says that nearby orbits do something also. So if you do this Markov process, you just prove that completely. So there's one reason why this Markov process, this Markov sim group is easier, is because the question is a different one. I'm just saying have now a theory that generates basically, it's a theory of time series of this equation, but only of one initial condition and then a probabilistic description of the future. But it doesn't say if two initial conditions, I ask like, when do these two initial conditions come together? There's no information in the model whatsoever, it's just gone. Yeah? So there's some good things about it because it's easier, and you can sometimes solve it. And then you can make some, using a core theory, you can make some probabilistic statements about this one of these trajectories, but not about two trajectories. And so usually this semi-group is then is a PDE in the usually SDE is a Fokker-Planck equation, and people can solve this sometimes. Give some examples. And so there's a big issue here that 1-point motion, 2-point motion are possible. So that's something that I learned at Unicamp, for instance. That this is an issue that's very nice. Things known about it, but very few people study it. It's ridiculous. So even not in deterministic systems, people don't study 2-point motions, almost. Yeah, okay, so then when we can do things here, okay, this is what we can use a kind of theory and say lots of things about this one-point process. I just like to now discuss some examples. Basically, I will just talk through some issues of random systems just by example, just to make some points. So this is based on some paper of some years ago. So this came out in 2007. I started looking at random systems in 2007. It's a bit, I'm a bit slow. But now things are coming out. So this was a paper where we looked at, here's the following problem. We just have an SDE. It's a really simple SDE. It's an SDE which is gradient. In fact, it is gradient. Here's the potential, here's a different potential. For one parameter, I can have a unique equilibrium or have this kind of pitchfork situation, one unstable, two stable equilibrium. That can't be easier. And okay, so to get the differential equation, now this textbook. Textbook is that you can immediately calculate stationary measure for this SDE because it's formula. It's just that you go minus the potential this normalization factor and so on. It's just textbook thing. So this Markov semi-group, this Fokker-Planck equation is easy to solve. So job done, right? Job done. So here we have stationary distribution, unique maximum for the when we have a local minimum, and if you have this other thing, we get this bimodal distribution. Good, so I look at Arnold called these things phenomenological bifurcation. I have some problems with that, but I'll not talk about it now. But here's what now I do. I now take three initial trajectories. And I just run this equation forward to three initial conditions with the same noise realization because it's just a random dynamical system. I think of it as something driven or something. So I take the three initial conditions, but I see that over time these things converge to each other. There's nothing in the Markov semi-group that can even know about this because there's only one trajectory. But it turns out that in the system, if you start with infinite condition, yeah, this orbit depends on noise realization, but actually all the initial conditions go to the same trajectory, and the trajectory is a function of noise realization. So we have basically an attractor, we call it a random attractor. It's a random point attractor, and so it's like a moving target. You know, the noise makes the target move, and all trajectories run after that target. This is a very typical situation, very simple dynamics. So it turns out that you can calculate for this equation, you can find the Laplace component is negative, and then with some additional arguments you can see that this actually implies this kind of convergence behavior to a unique random fixed point. But this is a dynamics, a random dynamics model. It's the simplest random dynamics. Like in ODE, the simplest dynamics you have a fixed point, and everything converges to this fixed point. In a random system, it shouldn't be a fixed point. It's very strange to have a fixed point, an equilibrium, but you can have a random equilibrium. That means the equilibrium depends on the noise realization. It is non-autonomous, it moves forward in time, but all trajectories tend to end up in this. Okay, so that's okay. So one way to look at this is also, if we have non-autonomous systems, it's bad to take the limit of time go to infinity because I don't know the noise realization, I don't know my driving at time in infinity. So that's a nonsensical question almost. But what you can do is also, you can also think of like, well, I take evolution, I add the negative time, and I say, well, what if I start a long time in the past and I go to the present? Because of our equations, it's what happened recently. If it affects the dynamics more as what happened a long time ago, and we can have pullback convergence. So many times in non-autonomous systems, people look at this pullback convergence. So in this case, for instance, the pullback convergence, if you fix the end time, it will be just 1 point. It means that everything that comes from the past converges to exactly 1 point. You need two-sided time. It's just it's a concept. Often, there's some subtleties in these notions and what doesn't get into them. Anyway, so Carl Flanderly wrote a paper in '98, and that caught my attention because they basically said, like, look, if you have the situation that we just described, that we have a bifurcation, it's either change of the sign of alpha, that goes for unique minimum or the double well potential, then we always have a unique point attractor. But that's true by what I said before, because they basically have a negative diagonal exponent and things. And this is what happens. You have almost surely is that if you take two initial conditions, you take the flow of those, they will go to 1 point. So the distance between these points goes to 0, time to infinity, almost surely. So they said, oh, that's interesting because you had a bifurcation when there was no noise, and now we switch out ridiculously small amount of noise. This sigma could be 10 to the minus 25. Then immediately I lose my bifurcation because instead of having two attractors, I only have one attractor. Now that's strange. Right? I thought that's strange. So someone told me, said, look, there's nothing to do here because noise destroys bifurcation. It's done. Turns out it's much more interesting than that. It turns out that the dynamics of this synchronization is complicated. So if you have a unique minimum, then we basically have some kind of unique, we have uniform contraction in a non-autonomous way, and yes, you have a unique attractor. But if we have this bimodal potential, what happens is that we have some region in the phase space where actually two trajectories diverge. We have basically non-uniformly hyperbolic dynamics. We saw some examples in other talks earlier. So what you get a diagonal exponent that gives you some exponential decay somewhere, but we get also some kind of constant. And unfortunately, if we have dissipation, we have some kind of competition between attraction and contraction and expansion, and then this constant will typically depend on omega. Omega is a noise realization. So it means that almost surely, for almost all omega, I will converge, but this number can go to infinity. There's no upper bound. So we don't have uniform convergence. So what I learned from that is that, convergence is nice, almost sure convergence is nice, but not uniform convergence is basically almost, well, pretty bad. And very many interesting things happen. So it turns out that we can actually classify this in terms of dichotomy spectrum, which is again the thing that also is studied in the non-autonomous setting quite a lot. And so, yeah, so we see how we have really different dynamics, and I'll give you some examples. But there's other kind of ideas, like for instance, topological conjugacy. You can also define a non-autonomous conjugacy. It turns out that these two systems, without playing slightly different dynamics, are still randomly topologically conjugate. There's good questions here about what notions of equivalence are the reasonable ones and so on. But let me first talk a little bit about these dynamics here. So here is the this is about graphs. But let me tell you what these graphs are. So here's alphas minus 1. This is basically the fact that we have unique minimum potential. And here's the finite time diagonal on the spectrum, which is proved by some experiment. If I take time to infinity, this becomes a delta function. And so here we have some time, and here I think it's longer time, where it just shrinks to some points. Here it says negative diagonal exponent is uniform. But in this case, we have some kind of like positive dichotomy spectrum. We have a saddle point, a repeller, and now what we see is we get convergence of this distribution to to a point, but actually there's always support on the positive side. There's always some expansion, because it's by positive probability we can see expansion. I can use my noise realization to just end up on this settle point and get expansion whenever I want. Yeah. So it's interesting. So although you have a convergence to negative diagonal exponent, you also always have support here. It's only in the limit that the support is not there, but everywhere else you have this support. So you have, this is typically kind of non-uniform hyperbolic dynamics feature, and that means that it's observable actually whether you have one type of dynamics or the other, because this is just something that can be observed. I just did it here in an experiment. Yeah. Now if you look at the two-point motion, I talked about it before, so we can think of the two-point motion by just looking at the mapping where we just two times the same map say, well, that's boring. If you just know the one mapping, why would do 2 points? But it's not trivial. So here we have the system on the line is with two attractors and a repeller. And here I do the phase portrait basically for the ODE. That has then also kind of like here attractors. It has some attractors here. It has some settle points here. This is a repelling point for the 2-point motion. But if you do the noise is now, it's the same for both things, means that the noise is only kind of like singular. It's only in this direction. So all my friends doing SDEs, they hate this kind of thing. Can't solve it. That's diffusive. But you get the interesting behaviors that you get systems that converge, say to this diagonal, which is synchronization. But if you're on the diagonal, you can always move towards this point, and then you can escape again, and you can go back. And that's the reason why you have this non-uniform behavior. For every point, if you're very close to being synchronized, there's always positive probability to be synchronized. It's only in the game of very long times that you get this almost sure convergence. So one has to be very careful.
What do you mean noise direction?
Well, the noise direction. So if you have there's two particles, right? X and Y. They experience the same noise. So if you think of the noise as a perturbation, this perturbation lies always in the direction of this, because it perturbs X and Y exactly in the same way. It's just in the same system, and this is so the noise factor will be like 1/1 or epsilon or something like that. So this gives you a stochastic process on the 2-point process, which is difficult to study for these reasons. Okay, good. So here's that basically the message here is that even if you can solve the stationary measure for the ODE's SDE and so on, you think you know everything. I would say I'm still working a lot on this problem to try to understand what is the dynamics actually of this non-uniform synchronization. It's quite interesting. Good. Another problem here is shear-induced chaos. Some people wrote some papers about it. I'll mention some. Here's a Hopf bifurcation. Everyone here knows Hopf bifurcation. Yeah? I'm just adding now, I'm just being nasty of going out of your comfort zone. Put some Wiener process there. And now it's again very nice because it's again a potential problem. I can just write down explicitly the stationary measure. And what's interesting is here is that there's a B here. B means some shear. Some shear means that the rotation depends on the radius, and there's not here. So alert is that we have some stationary measure, no B. Okay, now we look at the phase portrait. We know all these things, and now here's a plot of the stationary measure. So it's not so strange. We have a unique maximum here on top of the equilibrium, and if you have a limit side, you get a nice kick shape. All good. But now, if I change this B, my magic parameter, that doesn't change the distribution, I can get two kinds of dynamics. If B is small and I take this pullback picture, so I just run things from the back, I run them forward, I just go to 1 point. Nice synchronization. If I make B large, I get, looks like a Halon attractor. I get something here which is conjugated. And yes, what's the issue here? Here we have negative diagonal exponent, here we have positive diagonal exponent. This object is a snapshot of a non-autonomous attractor, which is chaotic attractor. Okay, so what does it look like? Here's a picture where we just run lots of initial conditions forward. The picture by movie by Dennis Kemnitz from Berlin. And the blue circle is just the limit cycle, this is for reference. And you see that so it's a non-autonomous attractor, it depends on time, but it has a lot of features that we recognize also in deterministic dynamics. It does stretching and folding in some way. And there's some, you can prove in this kind of setting that almost surely you have kind of reasonable properties of this of this attractor, this non-column attractor.
You don't understand the difference between these two keys. You show the P20 and the P1.
Okay, no.
What happened to the P1?
Yeah, if B is small, so what happens, I just take points in the far past, I run them all forward, they all go to 1 point. It's the same with synchronization and so on, the double well potential. I take different initial conditions, they all go to single point. But here they go to distribution of points.
Oh, B in the original equation.
B was shear.
The shear.
It said basically how the angular speed depends on the radius. So this is light shear, this is small shear. Small shear synchronization, light shear. So with light shear, what happens? We get this stretching and folding is caused by shear. Sorry, that was not this. Good. Yeah. So one other issue, kind of like if we do this thing with ergodic theory, we get this basically global picture, and this is also in the deterministic case. So we go to this ergodic theory, and then we have some statements that says, well, if I wait long enough, my orbits go all over the stationary measure, and I see some things at some point, and that may be useful. The problem is that, of course, there's no dynamics in this ergodic theory. There's only kind of like statistics of observations along orbits, which could be the thing that you're only after. But it's very difficult to understand, like, how do you actually move, even on an attractor, around based on ergodic theory, because it basically aims to average out things over infinity. So one thing that one can do is we can try to kind of study the random dynamics, and that's a nice setting, where you just basically constrain the system. In a local system, you say, for instance, they're in almost invariant set. They almost don't go out of a certain region, and say I just want to do statistic for the orbits on the condition that they don't leave. So every time an orbit leaves, I say I'm just throwing them out of the statistic. I'm not interested. I want only the statistics of surviving trajectories. But it looks complicated in general. It's complicated, but there's some good assumptions. This is possible. And so we come here to this topic of condition diagonal exponents, and also Matthäus here is a real expert on this almost probabilistic questions, the existence of relevant measures, and also this diagonal exponent. But the question is, like, if you now constrain a process to not escape from a certain region, can you still talk about dynamical quantities like, for instance, diagonal exponents? But I'm a little bit out of time, so what I'm going to do is I'm going to say that such measures exist, that say something about these things, that the diagonal exponents can be defined. I'm just going to give you an example here to see that it makes some sense. So here's a so-called Bautin. It's a Russian person with a French name, so it's unclear if it's Bautin or Bautin. But I was corrected by my Russian colleagues that it's really Bautin. I think it's from the British Institute of the World. Anyway, so here's the situation. This bifurcation is a degenerate one when you have two limit cycles appearing. So this is now stable, unstable, and stable again. And I'm just going to do the same thing as with the Hawk bifurcation. I'm just going to add some noise. And here we see stationary measure. It has some kind of like nice picture. But you can actually study dynamics. So here we draw the limit cycle, which is unstable, the one in the middle. And it turns out that the output exponent of this thing is positive, the global one. But it turns out that the conditioned output exponent for trajectories that don't leave this area is actually negative. So this, I started with two initial conditions, and they have a little tail, so you can see what they're doing. And what turns out is that when you're inside this region, you basically don't see any dissipation, but only when you're outside, the trajectories diverge. And I'll repeat this movie once. It's useful. So here we have two initial conditions. You see they get contracted to each other. Now we don't see anymore they're different. But the dynamics is such that you have synchronization in this region, but only when you go out, you desynchronize. So why do I show this picture? Because this is dynamics. This is what we do in dynamics, right? But this is not what stochastic analysis does. The stochastic analysis will say that in the end you will diverge. But if you stay here for 1 million years, then who cares? Yeah, but you do outside. So it is just, these questions are relevant, and they're potentially important also for applications. Okay, good. Well, there's other problems one can do. I don't really have so much time, but I want to click forward to something which I close to my heart is like bounded noise. So in most settings of noise, people say things are Gaussian. I love Gaussians, but they're not generic. Yeah, they're not typical. And there's a huge issue with also these SDEs and stuff that have been in process. They're definitely not generic. They're very special. So if someone is in a biological lab, writes on some things, writes an SDE because they're really sophisticated, have to be careful. There's naive ways of doing noise, like just bounded noise, just this what I said, these iterations with some small perturbation. You can also do in an ODE context. And the question is, what can you do? What kind of new phenomenon you get that you don't get in the SDE setting is that you get invariant regions. You get a topological theory of invariant regions that change if you change parameters. So let me show you some movies with this. So what you can do is you can look at the dynamics, you can follow the dynamics as a number of noise realizations, like a topological version of the Fokker-Planck equation. And you can see that you can ask, are you trapped somewhere? Okay, here's a movie, this is simulation. So the red region is an attractor, it's where orbits get attracted in the random system, and the black region is the domain of attraction of this attractor, and the white region is something else. It's like some other color. So we did this kind of number of simulations, and I don't know, here, singularity theory people have said, you look at this, you say, well, it's not that bad, right? It looks like a nice shape, and the shape seems to continuously change, but sometimes it just jumps, sometimes it just explodes. So it lends itself for something. Let me just give you one more picture. It gives you, can you prove that this changes in a continuous way, this attractor? Actually, it has some little singularities on the boundary, unfortunately, not always smooth. But then when it hits some boundary, the whole thing explodes. So we're running a project at the moment with how also with Constantinos Polioros, who used to be at USP and PhD with us, now back in London, to try to understand how do these things behave? Is there a theory? And it turns out that it's all related to some kind of like contact flows and stuff like that. So there's some things known in the continuous time setting, I think not so much in the discrete time setting, which is also linked to control theory. These sets also look a bit like reachable sets for control systems, because if you have a system, you just add some parameter in a bounded way. So there's a geometric theory possible here, but again, we want qualitative theory, and we also want to compute these things. Now, the problem is that this is a centralized problem. So centralized dynamics looks very nice. I showed you some pictures. Very difficult to do analysis, because the space of all subsets of, say, the plane is a horribly large space, has not a good structure. I cannot even do a implicit function theory. You know, how can I prove that I can continue an object? How do I do a bifurcation theory if there's nothing there? So it turns that we can actually, if you are careful, you can actually define a finite dimensional dynamical system that describes the boundary. That's not obvious. That took us a long time to get there. And it turns out that we can actually map the boundaries of this set, which live in an infinite dimensional system where I don't know how to do analysis, to some kind of like invariant manifolds of a low-dimensional system, which now I can just use all the usual hyperbolic theory and so on. So I can get structural stability of these sets. I can also understand bifurcations and so on. So I'll show you a picture here. So this is the same picture, but now you see some curves on top of it, and these are kind of associated points, fixed points, periodic points, of an associated dynamical system that lives actually in 3 dimensions, where this is a projection. And it turns out that I can continue these guys very nicely, because it's just usual continuation of invariant manifold construction. And then you can understand also bifurcations in this setting. Sorry, this is sure. But that's what we like, right? We like to kind of like use dynamical system theory to kind of make difficult problems more understandable. I want to show you this one picture where we have a bifurcation coming up, the next one. So here, this bifurcation where we had this, this black set kind of breaking up. You see here kind of a settlement bifurcation. New manifolds appearing, and these manifolds become the boundary now between the domain of attraction of this centroid system and these other things. Anyway, it would take me a long time to explain that. I just want to flag this as possibilities. There's a lot of things that can be done. The questions, I think, are very natural. It's not that I'm trying to sell some sophisticated technique, but I think they're non-trivial. But of course, if you look at the history of what we've been doing in dynamical systems, verification theory, and so on, there's also things to do. Now, other things that I didn't describe, which I'd like to just mention 1 second. For instance, if you have positive Dynamical exponents, we think of chaos, but in a random system, what's chaos in a random system? What is the definition of chaos in a deterministic system? It refers to things like periodic orbits or topological conjugacies or something. Can you do this for random systems? So this famous theorem of Kathok that says that if you have positive Dynamical exponent and recurrent dynamics, unless it's just a periodic orbit, you have a horseshoe. That's a wonderful result. So it turns out that there exists something like random horseshoe in random systems. So there exists actually topological dynamics, which looks like horseshoe dynamics, which depend on the noise realization, so it's a random object, but it has very similar properties to that of normal horseshoes. The problem here is that random systems don't have periodic orbits. So we have a random horseshoe, but it has no periodic orbit. That took us a long time to understand what's that. So we don't need periodic orbits for horseshoes, we just need hyperbolicity. So what do we need for hyperbolicity? We need to kind of control derivatives. But how do we control derivatives? We control return times. That's almost become reasonably often about reasonable times. You can measure contraction and expansion, and you can set things up in such a way that we can actually kind of see that real chaos appears in terms of stretching and folding. And so we don't need these periodic orbits. It's just like in the autonomous case, the periodic orbits are there, so why not use them? Because the return time is constant. If the return time is constant, you find fixed points for the return time, you get a periodic orbit. But in random systems, you can't. So that's work of the Dynamical, our PhD student work at the moment. I'm very excited about that. Anyway, many interesting directions, many open questions. So thank you very much, Michael, Tony. Thanks again for being an inspiration. We talked many years about I should do some stochastic things. I'm happy that it was possible to do something. Thank you. Bye-bye.
Question or comments? Thank you, Riero.
Do you have a PD for this bounded noise problem, or like you have Fokker-Planck?
No. You can describe these things look like a bit like oil spreading and this kind of stuff. So there are PDE formulations where you just look at moving fronts. But we're here looking is we look at the limit point where you have an attractor. As far as I've seen, there's some problems with that the PDEs will be ill-defined, because usually you look at the time you arrive at a certain point that they are level sets of the PDE or something like that. So here there are many that will be infinity, because if you're an attractor, the rest of the space will never be attained. So it's not that easy. There's some links between some PDE theory that people use for, say, wave spreading and stuff like that. But they're very special cases, and there's also very little, if none, geometric theory there. So there's about like numerical solutions of some kind of PDEs that in some reasonable setting give you something nice. There's usually some infinite spread of something. But this, I mean, that do I know of. And of course there's also the associated kind of Hamiltonian theory of these things in the geometric setting. So what we're trying to do is basically, combine these things. As far as I know, this is also all usually in differential equation setting, and not, for continuous diffusion, and not for discrete. So there's some issues there that not everything seems to be as nice in continuous time cases and discrete time cases, even though it can all be done. Yeah, so there are some links there, yeah, for sure.
More questions or comments?
Nice talk, nice propaganda too. I know almost nothing about stochastic dynamical systems, but I'm always interested in periodic solutions, attracting periodic solutions. But if I understood well, it does not make sense to look for periodic solutions in this context.
Now, periodic solutions, you can think of this as something to do with the symmetry. So periodic solutions, you basically see systems that should expect to see only a system that has some time shift symmetry, some periodicity. Otherwise, it's very strange. And equilibria should only be seen in systems that are autonomous. So you have to kind of like divorce from these objects you like. But when you get down the other side, it's also fine. Yeah. But there's some interesting question here, for instance, like how do things change? For instance, we have this region from synchronization to chaos in some sense. And that looks like instantaneous. You have a pointer tractor, or you have some complicated tractor, and it goes instantaneously. So we are looking a lot at that, and that's kind of interesting. But these things can be done. So even though you don't have the bifurcation scenario with simple periodic orbits and so on, you can still try to understand things. And Douglas yesterday talked something about infinite ergodic measures. Bifurcations from negative to positive diagonal corner through zero diagonal corner have to do also with infinite measures for the two-point process. Why? How can you see that? Well, if you almost synchronize, then 2 points tend to be very close to the diagonal. They spend such a long time there, and you get intermittency into 2-point motion and so on. So there's a lot of links there for stochastic dynamics. And it could also be done, of course, for also with deterministic dynamics. I keep saying to people also look in the deterministic setting. There's also this. It just in sometimes with noise, you think it's a little bit easier. So the nice thing of adding some noise. So many people say I got a theory in deterministic systems. The big question is like, what type of invariant measure do I have? Because you have many of them, and you don't know how to choose between them. So if you just add some diffuser noise, this problem becomes trivial. And now, what to me is then the surprise or the disappointment that when you know the stationary measure, you say, so now I know the dynamics. No, you know nothing about the dynamics. So this point where people got stuck on an ergodic theory, where they say we want to know the nature of invariant measures, that's nice, but it doesn't really tell you what the dynamics is, because in my random systems, nice measures are for free almost, if I add nice noise, but then I still don't know anything about the dynamics. So I think that there's a certain problem with the ergodic theory. Not that it's not a great problem, but the problem is that you can't just do only ergodic theory, then don't ask any dynamics questions anymore. That's also maybe why some people become not interested, because they say, well, what are you going to tell me about this thing? So, to me, it was a surprise. Yeah, but that's good, I think, also to try to do things out of your comfort zone. Just go and have a look around, and you make some interesting observations. And of course, I'm not the only one making such observations. Anyone that would do this would probably come to see.
Okay, thank you.
It's true that when synchronization occurs, and the orbits that the convergence orbit is it can be visible to the orbit of the system without noise.
No. This is the thing. So there's nothing comparison with the deterministic system. It's not like small noise and we have almost deterministic dynamics. It's the wrong way to think. It's a stupid way. You have something in fibers and you run between different fibers. Yes, of course it's interesting to know some things about the deterministic system in single fibers, but it will not tell you what the dynamics is unless you make the noise very small. So then you have, of course, strong correlation. The real question is now, so you see different phenomena, you see real different dynamics. You don't see the, for instance, like transition to chaos is not via period double X. It doesn't happen. So, but you see intermittency, for instance. So that does so.
Yes, I wonder if you can answer this one question like this one. That assume you have a planar local Terra system, and you have an additive noise. Then can you prove persistence of the system, meaning that with this noise you never arrive to extinction? Only this can not.
Well, depends on the noise, of course.
And with additive noise and.
Yeah, but if the problem is that, for instance, in this SDEs, it's the Gaussian noise is such a way that with finite probability, you can jump as far as you want in as small time step as you want.
So, for this reason, and with bounded noise.
Yeah, bounded noise you can do things and you will get confinement. Yeah, and I'm interested in that. But the problem is if you do bounded noise, you lose the setting of the SDE, which says that you have a markup process basically, so you need to do something else. But it's still very reasonable. It's very reasonable to make a system which is even a Wiener process that drives something. You bound it. For instance, you take the sine of the outcome of a Oyster-Rudbeck process, for instance, and then you just put it in your equation. It's just not technically an SDE. It's just another structure, but it's a random dynamical system, I would say. But people seem to be not studying that because they insist that the integration step basically is independent. Marco, it's not necessary. It's nice because then you can compute some things. I'm all happy about that. But as a modeling assumption, it's quite stringent, and that's why we get also this, non-differentiable noise realizations. It's not because the world is like that. It's because our mathematics is like that. Otherwise, we can't do anything. So fair enough. Fair enough. Great invention. But now we have computers. Why would I try to simulate a Wiener process on a computer, which is really hard? And I can do something else, which is a lot easier, and the theory still would work. Yeah. Clearly, I'm very interested in looking at these low-dimensional examples, like for instance mathematical biology and a lot of there. Look at bounded noise. So we do, so our students are looking in this direction. Yeah.
Hello, Alice. Thank you very much for this talk. In general, I try to avoid noise, but I start loving it when I see the results. I just wanted, in the Hopf case, in a certain sense, when you go to an attractor, it resembles a little bit what happens when you have a slow passage through Hopf bifurcation. Is there any link? Because in a slow passage, you just change your time slowly. Here, in time, you do movements, and with the B small, well, in slow passage, indeed you synchronize in a certain sense everything that comes from a little further. But then, of course, you
I've not thought about it. I'd love to think about. Yeah, I've not thought. Of course, some people also do say stochastic differential equation in slow, fast settings, and so not really looked at that so much. But it's of course interesting to make these links. Yeah, if you see something very interesting to learn, and see if there's no, but it is. There's of course some hallmarks of here, but I think what this Hopf bifurcation point is actually a very hard one. So we have not managed to prove. We have managed to prove at some point that there's such a transition, not exactly where it is. Another interesting, I think, modernistic approach. Then with computer-assisted proof, you can actually prove 10 to the minus 5 close where the bifurcation point is. And that's another thing which I think is also for our younger members of the audience. What you can do by hand is one thing, but there's some fantastic computational methods nowadays where you can really add things, because there's a lot of work like Freddy's doing for years, and he writes 200-page papers and so on, or you write whole books, monographs. There's some things you can do with computers that can also, for specific problems, really do things that you can never do by hand. It's so difficult to do the estimate, but computer-assisted things can be done. And this is something that's upcoming, and I'm very happy to have PhD students that are excited for doing this, but it's still a marginal thing. I think this will become really relevant, will become relevant for applications, because you want to go with someone. We believe in this model, and here is some rigorous estimates of say safe regions or some kind of like, and not like, well, of course, non-slopey simulation is also okay, but from a legal point of view, if you can make them precise, we can make it a theorem. Yeah, so there's just recent work with Hugo Schuh. We managed to, for instance, to prove that for these equations that the curve you plot, the sloppy computation is correct curve up to 10 to the minus 5 or something. But that's a lot of work still, and you need to be smart how to do it. But I think that over the next few decades, this will become more routine. Very, very interesting development, I would say. And also how to link up theoretical stories with, applications. Anyway, sorry, I just dwell off your question. More propaganda.
So let's take this speaker again. Before the coffee in the poster section, we have a special talk now by Marco Teixeira.
I take just 2 minutes. Yesterday, Enrique Ponce from CMedia told me que semana tão inolvidável. Yes, for me it's the same. I think this the last week was unforgettable because you know everything why. But I take the time now to say many thanks to the organizing. That is fantastic, the organizing of this Congress. And then I would like highlight also the performance of Lucas, the postdoc who was working here, and the students that is a phenomenal performance during the Letícia, Lúcia, Eduarda. And then thank you. Okay, then I would like to ask you for a round of applause to the organizers here.
So now we have this.
Thank you. So I'd like to first thank the organizers for making this event in honor of Professor Marc-Antoine, and also for giving me the opportunity to present here. So what I'm going to present today is part of the work that I developed during my stay in Belgium with Carl Gross-Verma. And we studied linear dynamical systems. So in linear dynamics, we are interested in studying the dynamics of linear composition of linear operators acting on topological vector spaces. And for example, we can study the orbits of these operators, orbits of points under the action of linear operators. And we can define many kinds of chaotic behavior for study. For example, we say that an operator is hypercyclic if it admits a point that has dense orbit on space. And we can also study the notion of topological transitivity. We say that an operator is topologically transitive if for every pair of non-trivial sets U and V, there exists a natural number n such that Tn of U intersects V. So, image representing these notions. In hypercyclicity, we have a point X that visits every set under the action of T. And in topological transitivity, we have that given two open sets U and V, there exists a natural number such that Tn of U intersects V. And by virtue of the transitivity theorem, these two notions coincide in our context. But we can also study stronger notions of chaoticity, such as mixing operators. So we say that an operator T is mixing if for every pair of non-trivial sets U and V, there exists an n0 such that Tn of U intersects V, but now for all n greater than n0. So now instead of just visiting taking the set U intersecting V once, we require to intersect V for all natural numbers greater than some number. So, and then we have a very useful tool to show that an operator is mixing, which is Kitai's criterion, proved by Kitai in her PhD thesis. So we say that T satisfies Kitai criterion if T satisfies the hypothesis of this theory. So suppose that we have an operator acting on a separable Banach space X, and suppose that there are dense subsets X0 and Y0, and a map from Y0 to itself, such that Tn of X goes to 0 for every X in one of the dense subsets, Sn of Y goes to 0 for every Y in the other dense subset, and S is the right inverse of T in this Y0 subset. Then this theorem tells us that the operator T is mixing. So one can ask if the converse is also true. That is, if we have a mixing operator, if it satisfies this hypothesis. And the answer given by Sophie Griveau, she showed no. That no. We can always, in every separable Banach space of infinite dimension, we have that there exists a mixing operator that does not satisfy Kitai's criterion. But for many classes that we know, the converse is also true. And now let me give you a couple of examples of linear operators with interesting dynamics. So we have two classical examples are the Rolodex operators and the Riemann operators. The Rolodex operators are the shift, where we consider the sequence space with some weighted sequence space. And it's possible to show that this operator is mixing if and only if lambda is greater, has absolute value greater than 1. And the other examples are the Birkhoff operators or translation operators acting on the space of holomorphic functions on the whole plane. So we take some A different from 0 and take the map is simply the translation. And it's also possible to show that TA is mixing. And one way to do so is to show that they satisfy the test criteria. And these two are composition operators, or sometimes called Koopman operators. And as we will see, one can study composition operators in many different settings. And the one that we studied was introduced by Bayer in 2018. That is the setting of spaces of measurable functions. So suppose that we have a sigma finite measure space and a measurable function in the space. We consider the composition operator acting on LP of X given by the function that takes phi into phi composed with F. And when they introduced this notion, this session of studying composition operators on spaces of measurable functions, they were able to completely characterize composition operators that are hypercyclic and mixing in terms of the measure and in terms of the function f. So hypercyclic characterization is the following. We have that Tf is hypercyclic if and only if for every epsilon greater than 0 and measurable set A with finite measures, there exists a set B inside A and some K such that the measure of A minus B is smaller than epsilon and the kth preimage of B and kth image of B are smaller than epsilon. And the mixing one is analogous, but now instead of only one set B and some K, we have a sequence of BKs and some K0, so that for every K greater than K0, we have analogous conditions. So this is more or less what's happening. We have each set A, a finite measure, and then we can find a subset B inside A, such that when we iterate K times forward and backwards, supposing that it's dynamical, for example, then these two are small. And what we did is we were able to characterize the composition operator satisfying p-test criteria. So now instead of the measure of pre-image and image of B being small, we must have that they go to 0. And this is the complete characterization, also in terms of F and the measure. And by doing so, we were able to find some explicit example of a composition operator that is mixed and does not satisfy p-test criteria. So we will try to give you an idea of the proof. The space that we consider is the product of the intervals 0, 1. And F is more or less their identity. It takes one point from one interval to the equivalent point, of the point to the next one. But we consider different measures in these intervals, and then the measure of the whole space will be given by the product measure. So in the first interval, we consider simply with the Lebesgue measure. Then we divide the Lebesgue measure by 2. So this whole interval has measure 1/2. And then we consider the first half of this interval and expand it by 2. So we consider the Lebesgue measure lambda here and lambda 2 over here. And then again, so that this first half has measured 1, and then we go backwards until the whole set has measured 1/2. And then we do the same with the second half of the interval. Then, until we get again to the interval with Lebesgue measure over 2. Now, we divide it by 2 again and repeat the same process for every subinterval of length 1/4 until it has measured 1. We go multiplying by 2 and contracting it by 2 for each one of these. And it's possible to show that it is mixing because the big case that we consider will be the complements of the sets that we are expanding and contracting. And it's also possible to show that it does not satisfy Hittite's criteria. Because if we take A to be this first interval, for every B with positive measure, a relatively big measure, it will intersect some interval of the form of R2. So the measure will be eventually big. So it cannot go to 0 if we take some B. Okay. I hope this gives you some intuition of what it is. These are the references for this talk, and thank you very much for your attention.
Thank you, Daniel, for this very nice talk. So we have time for questions or comments. So no questions. So let's thank the speaker again. We have 2 minutes. So let's continue with our next speaker, which is Renata Possobon. She will talk about geometric properties of disintegration of measure, and Renata is from Unicamp. So please.
Thank you. So thank you to the organizers for this wonderful workshop, and thank you for giving me the opportunity of being here today. I'm going to talk about the geometric properties of disintegration of measures. That is a joint work with my advisor, Christian Rodrigues. And nothing better than start by understand what is the disintegration of measures. So given a probability space, we can take a partition of this space into a finite number of measurable subsets that have a positive measure. And then for each element of this partition, we can define a measure, μi, like this, for example, and then we can write the initial measure as a combination of this family of measures μi. So this family here is a disintegration of mu with respect to this partition. More specifically, when you have a probability space and a partition of this space in measurable subsets, we can use this natural projection that takes one point x and associate with the element of the partition contained in this point to induce in the partition structure of a measurable space. Just saying that a subset of this partition is measurable if and only if this pre-image is measurable on X. And then we have a sigma algebra on the partition, and we define a measure on this partition by pushing forward the measure mu by this map hoop here. So a disintegration of mu with respect to the partition is this family indexed in the elements of the partition, such that the measures are concentrated on the element on which is indexed. This application is measurable, and we can obtain the measure mu again by integrating this family with respect to this reference measure. So this is a really powerful tool to understand local and global behavior of dynamical systems. For example, in ergodic theory, we can relate this directly with the ergodic decomposition of invariant measures, and this encode a lot of information about the asymptotic behavior of the dynamical system. In general, very little information is, geometric information is taken account when we study disintegration of measures. So my goal today is to advertise this viewpoint of tackling disintegration of measures, taking in consideration intrinsic structures of a probability space that are obtained via optimal transport. So what I mean with via optimal transport? The cornerstone of the optimal transport theory is a logistic problem addressed by Monge on 18th century, something like this. That the idea is transport masses from one point to another one, minimizing the cost. So in a modern formulation, we have this Monge-Kantorovich problem that we use like two spaces x and y and probability measures on these spaces to modeling, like the pi of the sun here and the hole here. And we want to define cost to transport these masses here, and we minimize the total cost among all the possible transport plans in these spaces. From this problem, one can define natural distance between measures, just choosing this cost function as a power of the distance, and we call this thing the Varsity distance. So it's just the solution of the Monge problem, choosing this cost function as the distance between points. This is not properly a distance because this is not finite, but our way to solve this problem is just to do a restriction for the space of measures in which this value is finite. So we call this space a Varsity space. In optimal transport, this Varsity distance incorporates a lot of the geometry of the space X. So with this, we can relate the distributions on X and on X with the geometry of X. So this is the idea here. So we have three main results. One is a disintegration theory, a rigidity condition for absolute continuity of conditional measures, and we establish a geometric framework on which we can use the disintegration to classify somehow the foliations of a manifold. These are in these two papers. This is published, and this will be available online soon. So our first result is this setting that we will keep this in the stock. We take it X and Y separable, locally compact metric spaces, a Borel map between these spaces, a measure that is Hadron positive and finite measure on X, and then we do the push forward of this measure by pi to establish a measure on Y. And we prove the existence of a disintegration in this setting here. We also have a kind of a uniqueness. If you take another measure that is absolutely continuous with respect to this measure nu, then all the conditional measures here are also absolutely continuous. Using this idea of disintegration, we define the disintegration maps. That is a map that associates each point on Y with the respective conditional measure on the Weierstrass space, such that we can obtain the measure mu by integrating this function on Y with respect to the mu. So even though we can define it for every P, we are interested in P equals 1 or P equals 2. P equals 1 because we have a explicit formula for the Weierstrass distance and it's really good for calculating things. And P equals 2 because we have a really good geometric characterization of the two Weierstrass space in terms of the properties of the space X. So think about this. We proved some properties for these disintegration maps. First is one application like this for P equals 1 is a disintegration map if and only if it's a Borel map. Also for P equals 1, you have that this disintegration map is nearly weakly continuous, and with weakly continuous, I mean continuous in the Weierstrass space. If the application pi is bijective and continuous, then F is weakly continuous for every P. And sorry. And if we have a situation that's a metric measure foliation, what is this? We have a foliation on X that the distance between two leaves is equal of the distance of any X on the first leaf and the second leaf. And moreover, we have this equality between these distributions given by the disintegration of a measure and the pre-image of the respective indexes here. If we have this metric measure foliation, then the disintegration map is always weakly continuous. So with this idea of continuity of disintegration maps, we can prove something about paths of measures and absolutely continuity from disintegration maps. It's a lot of information. It's lunchtime. I know that no one wants to read it. So I want to turn it in something more visual. Better. So keeping the same setting. So we have this application pi here in our disintegration map. What we prove is that if this y is additionally path connected, choosing 2 points on y, we can find a path of measures given by the disintegration map on the two Weierstrass space. Moreover, if this space X is a smooth, compact Riemannian manifold, and our initial measure is absolutely continuous with respect to the volume measure there, F is a little bit special. We call this minimizing invariant, that take minimized path here and goes to a minimizing path on the Weierstrass space. And either the first measure here or the last one of the endpoints measures are absolutely continuous with respect to the volume measure on the manifold, then all the measures on the path also are absolutely continuous. Especially when we have then the disintegration, the metric measure foliation here. This is true for the volume measure on the fibers, on the leaves. Thinking about this kind of foliations, we can use the disintegration to understand better when we have a metric measure foliation or not. So we define this kind of derivative for the disintegration map, and also this energy here. And looking for this guy, we have that this is greater than or equals 1 everywhere. And the minimum among all the possible disintegration maps here, it's 1 if and only if this is 1 for all y. In this case, we have isometry between the versus side distance, this distance in x that I just put this notation here, dy. So one thing that we can prove is if my disintegration is full supported on the pre-image here, then we have the minimum of this energy equals 1 if and only if this family of pre-images defines a metric measure foliation on lens. Here, I'll highlight that this full support that we put like a hypothesis here is fundamental, since, for example, we have a disintegration on this ellipsis, and we took the measure mu such that the disintegration is these Dirac masses on these points here. Then we have this isometry, but this thing is not a metric measure foliation, since the distance is different between the leaves. In this sense, if we took the lambda is the parameter here for the ellipse, we took this equals 1, then we have circles as the leaves, and then we have a metric measure foliation. So this energy somehow can fill when we put some perturbation on the foliation. So as an example, if we model our space with this lambda, start with lambda equals 1 and then go increasing this lambda, we have this energy for P equals 1 given by the length of the circle divided by the length of the ellipses that I going when I go into increasing the lambda. So we have something that's growing smoothly with this perturbation in the foliation. So this is all that I wanted to, to say. Thank you for your attention, and once again, happy birthday, Professor Marco.
Thank you, Renata. I have some questions. There are some questions or comments.
In ergodic theory, we usually consider the set of measures that are invariant under some dynamics. And here you are also considering the Wasserstein space is also a set of measures, right? But if I understand correctly, there is no invariance under dynamics. So can they be related? Is there any relation?
You can use, for example, the disintegration in the sense of the ergodic decomposition. So we are doing a disintegration into invariant measures, and then we can use this general theory for this context specifically. Oh, Jesus. But here it's more general. We are not considering invariant measures.
Okay, thank you.
Are there more questions? So let's thank Renata again.
É só um minuto, ok? Obrigado. Acontece.
So our next speaker is Professor Daniel Palazzolo. from the Hotel-SAS University. He is going to talk about, and now I don't have the title of the lecture, so please.
I try to speak loud. Okay, so first of all, thank you very much for this opportunity to be here, to meet again some good friends and honor my audience. So I'm going to talk about this equation here. Well, let me start with the motivation. For dynamical systems, you consider a family of planar vector fields. Parameter lambda, and you see that lambda can be a multi-dimensional parameter, and you suppose that for, let's say, lambda some line is some neighborhood of the origin in dimensional space, and you suppose that x0 has a hyperbolic polycycle. So what's a hyperbolic polycycle? It's a configuration. Let's say one of the configurations that you find when you try to understand the Dynamical theorem. So a configuration formed by a collection of saddle points. It's a new hyperbolic. And then overcoming connections between the stable and unstable manifold curves of signification, which one is right. So I have this symbolized S1, S2, Sn, and each Sk is a saddle. Okay, so locally, we have your vector field locally given by some coordinates x and y by something like this. So here x minus ry y plus higher terms. Okay, where r is some strictly positive number. Okay, so of course this r is different for each one of these saddle points. And now we'd like to understand how this kind of object bifurcates by perturbation of the parameters. Okay, so we understand. So the goal is to understand the bifurcation of things. Since I'm going to germify everything around this configuration here, we usually say that we are going to make a, let's say, a semi-normal problem where we look at the family as a germ of bifurcation around this gamma, the hyperbolic polycycle. Okay. So of course you can imagine very many situations where, for instance, you have this two-saddle connection, and you can imagine that you break these connections between the saddles and create, for instance, another connection like this. Of course, and then you can bifurcate an n polycycle. So I call n polycycle when you have n saddle points, which you are n minus 1 polycycles, like this. And such kind of course, such kind of behavior is also interesting to understand. But our main goal is to, let's say, one of the main question that we would like to answer here is to understand how the limit cycles bifurcate from this configuration, right? So to compute, understand limit cycles nearby. Okay. So there's a very basic question that you can ask here before trying really to understand how this bifurcation occurs, is to try to answer the fully basic question: is there a finite number of limit cycles which accumulate on this configuration by, let's say, if you assume sufficient regularity for this initial family? So this is formalized by the notion of cyclicity. Okay, so we can compute the cyclicity of x lambda. So let me So you have to formalize this notion that you, nearby this configuration gamma, in the, let's say, in the product space, x, y, and lambda, you have at most a finite number of limit cycles to show up. So we usually write like this: you take the infinite of all k such that there exists a neighborhood u containing gamma on the, and another neighborhood, let's say v containing 0, such that, let's say for all parameter lambda on v, x lambda has at most k limit cycles on Q. Okay, so you localize, let's say, in the neighborhood here, and also in the neighborhood of the parameter space, and then you try to find the smallest possible number that of limit cycle that you can find inside. So of course there is a very basic question: is this number finite, right? So this is an open problem. Okay, if you are in the, let's say, in the smooth setting, C-infinite setting, it's easy to find examples where this k is finite. But it's an open problem for n greater or equal than 3. So I think it's proved by Hossain, the case of where we have just, let's say, one sample point, okay, proof, and then there's a proof of in the case of 2 of n equals to 2 by Gavrilov. But for it, as far as I go, for it greater or equal than 3, the open problem is to show that if x number is analytic, by which I mean that A and B are analytic functions of x, y, and lambda, then this equation is fine. Of course, this is one of, let's say, one of the questions that should be answered if you someday you went to prove given 6 problem. Of course, there is such kind of phenomenon which appears in polynomial vector fields, so it's inevitable to deal with this kind of problem. So I wish to mention that this kind of question, of course, has a very easy answer when you have, let's say, bifurcation of the set of the weak focus points, because in this case you can use the analyticity, the first return map, to show that the cyclicity is always finite inside. It's really a problem which is due to the fact that you have complicated behavior when you try to complete the first return map. Okay, so how do you deal with this problem? So of course you have to try to reduce and to understand, let's say, transform it into a one-dimensional problem. And of course you do this by this very let's say, classic Poincare first return map technique. So there's a result of Mortada which computes, let's say, a sort of expansion of this first return map under generic conditions. Okay, so Mortada says the following. So up to, I'm not going to let's say, formulate result in the old.
I'm sorry, there on open problem, if x lambda is what?
Finite. The cyclicity is finite. Analytic, sorry.
This word is analytical.
Analytic, yes.
Thank you.
Yes, because mostly particularly if, let's say, if this is a polynomial equation, then, but as far as I know, there is no really specification where you suppose that it is a polynomial vector, let's say x is a polynomial vector field. As far as I know, you cannot use this information here. Okay, so Mortada essentially gives an expansion of this map under generic condition that I'm not going to state. It says the following. So there is basically 2 n parameters which will play a role here. So up to our parameterization, I'm not going to state it very precisely. Up to a good parameter, a CT parameterization. Of a transversal, this is my transversal sigma. Okay, so this first return map, I'm going to call this P. This is the base point. So it's something like sigma plus sigma plus is just the positive part where we have the monod return map. So it has the following expansion. So lambda of x, so x is the parameter here, can be written as follows. So this is the title of the talk. Okay? So an plus an minus 1. I'm going to explain this. Yeah, so sorry, I'm going to write this equation here up to, so the equation p of x, p naught of x equals to x, which is of course the equation that will give us these guys here, is given by the following. So x plus f of x lambda. Okay. Where here each ai is a function of lambda and also the r functions, ck function. Okay, and this k can be chosen as large as we wish, up to reducing, of course, the neighborhood here. And most important, so there is this term here. It's very important to control this term, and this term is called fk. So there's a technical name. This is uniformly flat on x. I'm not going to define this precisely, but essentially it says that you can, when you start to let's say, take derivatives of this expression, then this f and all its derivatives with respect to x are small. Somehow they can be controlled. I'm not going to enter too much in the details, but for us the important thing is the conclusion. Let's say the consequence of this is that under generic conditions, generic condition is a condition that we give on the, let's say, on the family, and most in particular on the, let's say, on the zero parameter vector field family conditions. And the solution of this equation essentially we say that we can forget this function f, which appears. Okay? Correspond. Okay. To isolated solutions of this equation here, where now we forget this. Okay. A1 plus x to the power r1, r2, etc. rn equals to b times x. Okay. So what's the interpretation of these parameters here? So now, of course, here you can think of this as an embedding. So this lambda embeds my first return map into this more general family, where now I consider this a1, an, r1, rn as parameters, as free parameters, let's say, and b also. So what's the interpretation of this? So, well, I mean, this is quite clear. The r, which appear my polycycle here. Now I have unfolded my polycycle. So of course the r's which appear here are the ratio of the eigenvalues on each singularity. Okay, and then there is this breaking parameter a. So this is r1, r2, and then there is this breaking parameter which measures the distance between the stable manifolds of one of the saddles and the unstable manifold of the preceding one. Okay. So of course this let's say when you look at the equation this way, let's say sorry, and then there's this b, which appears and corresponds, roughly speaking, to the let's say, to the hyperbolicity let's say, the derivative of the first term for the unperturbed situation, and then this can be different from. So, okay, so now, let's see, we forgot the original problem and tried to find how to estimate the number of solutions of this equation, right? Because so what's the motivation here? Yes, as I said, when you complete the solution of this, we are not really solving the original problem because there is some disciplinary conditions which appear here. Right, so we're not really tackling this general problem here. But it is the following, is that you know that there is this Hilbert number, which we'd like to compute, right? And then there is the following thing. So if you have a polycycle, let's say, suppose that you find some mechanism to produce a lot of solutions of this equation. For instance, a mechanism to produce solutions that grow very, very fast with respect to n. Right? Exponential growth or something like this. You can show that you can produce a polycycle in a polynomial vector field whose degree is a linear function of n, which realizes this number of solutions. Right? So if you are able to prove that there is a mechanism to produce a lot of solutions, I guess you prove that this, let's say, this number grows really fast. So, I mean, as far as I know, up to now, all the lower bounds that you know for this number are computed by, let's say, perturbing integrable situations, right? So by taking, let's say, something which is nearby some polynomial, some Hamiltonian vector field or some integrable vector field, and then use the techniques of Dynamical function, etc., to compute the solution. But in some way, this kind of equation is very far from the integrable world, right? So you could expect that by looking at things which are, let's say, very far from the integrable world, you can find new phenomena. So this is that sort of motivation. So this is motivation to understand the solution of this equation. So now I'm going to define what we call the analogous cyclicity problem for this kind of equation. Okay? So now here, of course, I'm going to suppose that A1, AN are parameters. So R1, Rn now are also free parameters. So I'm going to suppose that they are positive. But it's not necessary. In fact, what I'm going to do is not necessary to assume that they are positive, but this is what comes from the problem. Okay, and then there is parameter B, which is also real number of 0. Okay. But from now on, I'm going to suppose that because this is not essentially different when the B is different from 1, I'm going to suppose B equals to 1 to simplify the discussion. And okay, so I said that this is a sort of approximation to the real solution, but if you are in the piecewise linear world, I know that people like this here, you can very precisely realize this equation here in the piecewise world. How do you do this? You just take, let's say, some decomposition of your space into cells. So this is, and on each cell here, you put a linear vector field, right, with a saddle point. Right, so take a saddle point here, and then I'll put another saddle point here, right? Create another cell here, and suppose that all these saddles are linear saddles, right? So in this case, of course, the Dynamical map, the transition map here is just this kind of map. And then there is, now you suppose that for the parameter 0, there is a connection between the separators of the saddle points on each of these cells. And then there is a parameter which moves just linearly each one of these saddles inside the cell. And then this is the breaking parameter which gives precisely this equation without any perturbation, right? Okay, so there's a piecewise linear model. Event with many cells. So one of the difficulties of the problem is that when you look at this function here, we don't see multiplication, but you see composition of some objects, right? So this is really something which is given by, it's an element of a certain group. So I call this word, I call this F A R. So this is the function A plus X to the power R1. R2. Yes. Okay. So this is my. So how does this? How do you form this word? So this is a word that form in a group. So this. Okay. So F is formed by composing. So there is a group of translations that X next to the X plus A real number. Translation, and then the group of powers. So the X goes to the power X to the power 9. Okay, so you compose successively translations and powers, and you get such kind of, right? So there is some, let's say, quite interesting. So first F A R, I could write it. Let's call this P R, this T A. So F of R, it's what? It's P R1. Compose as P A1 and so P A. So this is a word in it. So for instance, there is also some people in group theory which is interesting in trying to figure out the structure of the group that you form by composing translations. Like perhaps if I have time, I'm going to discuss a bit of this. So the question is this a free group? Is there some relations on the group generated by translations and powers? So we have this map here. But of course, there's a problem when you start to make this, taking this power, because you have to be in a domain where you, to stay the real set here, where you have to, where you're able to take this power. So these functions are not, of course, these are not globally defined. So it's important to keep track of the domain of F. So F A R is defined on an interval. So it's an interval this time, which is given by the following thing, French notation for with the interval. So it's given by intersecting the following thing. So it's R X or 1. So the following inequality should be satisfied. This X or R1 should be positive, and then we have X or R1 plus should be positive and so on. Okay? Because each time you're going to take a power, possibly a rational power or real power of this kind of expression. So when you take the intersection of all these inequalities here, you end up with an interval which is the neighborhood of infinity because of this condition. So what now I'm going to formulate that I'm going to call Fp and R. So this is the number of isolated fixed points of A and R. So remember that I'm going to take equals to 1 here on data of V A. So just count the number of fixed points. So of course this depends on the parameter. And now I'm going to call Fn the supremum for all possible parameters of Fp. So Fp for fixed point, of course. So this, of course, is the analogous of this the simplistic counting before. So I want to know if there is a uniform estimate for the number of fixed points. Let's say a finite bound for the number of fixed points of this equation uniformly on the choice of A and R. So in this case, the answer is yes. So this number here is 5. there's a, let's say, a very, this is a consequence of a very general result of Chovansky. Okay, so the basic idea is that you can transform this equation here to a system of n equations by adding, let's say, auxiliary variables, and then Chovansky theory is precisely the tool that you need to deal with this, the finite number of solutions of this system of equations. Okay. So this, let's see, since we get rid of the problem of finite simplicity, but now Chovansky series gives more than this because it gives you a bound, right? So we're going to give the Chovansky's bound. Work a little bit because this theory is for very general phenomenal system, but in this case you have this bound here. Choose upon 2n minus 1. N minus 2. Process is not very important to know this precise number, but the idea is that this number grows spectacularly fast with n. So most of people think that this is really not a realistic upper bound. And let's say one of the goals of my work was to try to improve this bound, right? And let's say to show that I have something smaller than a very, because this is much more than exponential growth. Here I have something of the order n to the power n, right? Like a tutorial. So let me just give you some bounds. Let's just to give you an idea. So it says that fp of 1, fp of 2, fp of 1 is. So this, let's say this is called the Chovansky's bound. So for n equals to 2, gives you 8. 500, 5,854. Okay, I will stop there. So this is something like 10 to the power 4. Unfortunately, we are able to compute this number for small values of n. And I go to say the real value of p of n. We know this number at least for up to order. Sorry, I don't know. One here. But fp of 1 is equal to 2. It's very easy because fp of 1, you're just, so you have the curve x to the power r minus a, and you're intersecting it with the diagonal. So it's either convex or concave, and then equals to 2. For n equals to 2, so now I have a word that 2 length 2, and the precise number here is 3. And for 3, let's see, 3 is a word of f3. We know that fp is equal to 5. So there's 5 solution here. And so, okay, so this gives you some hint of how this bound is not very realistic. And as far as I know, there is no knowledge of the exact value of fp of 4. So what I want to explain to you today is another technique to obtain this bound. So it's given by, it's another bound. I call it DD because it's derivation division bound. I'm going to apply a sort of derivation division algorithm to the word here and simplify it successfully up to arrive to something which is constant, right? So now they just use a sort of Rolle's theorem. And since when you, let's say, you start derivating this object, when you arrive to, let's say after capital N steps, you arrive at something constant, so you know that your equation has both epsilon. Okay, so this bound here, for explain it, I'm going to give you the results. It's very promising, this first steps, because there's a exact number. Okay. So the bound here for n equals to 4 is 13. I don't know if it can be realized. I know that this is also number bound for the number of set points. But unfortunately, for starting from n equals to 5, my bound is much worse than Hovansky's bound. It's not really. But there's another interesting aspect that you can get from this procedure that I try to explain it. Sorry. I missed here because for n equals to 5, we still have something which is reasonable, not realistic probably, but it's around 6,500. But for n equals to 6 here, my bound is a tower of 2 of height 600. Well, for those of you that know this, this is a. I later realized that this is a effect, the Ackermann function. The Ackermann function is a function which goes much worse than this. But at least for the, let's say, coordination part here, it gives some reasonable. But there is another thing that you can define. So I'm going to make a very simple explanation of this derivation. So what's the idea? Okay, let me just start with this very simple example. So we take n equals to 1, so x to the power r1 minus a, 1, and here you have x, right? So now, of course, I want to consider the function g of ar, f of ar, minus dt. So this is the function for which I want to compute the number of zeros. So for r equals to 1, this is my function. For n equals to 1, this is my function. So the idea is to get a monomial from some stage is non-zero, right? So I got the first derivation. So it's again r1, x to the power r1 minus 1. So I cannot divide here because there's a step. But then there is a second step. Second derivation. And then we get r1 minus 1, x to the power r1 minus 2. And now you can divide, right? Recall that we are in the region where this function here is positive. So I always divide it by something which is strictly positive. So I divide by x to the power r1 minus 2. And again, r1, r2, r1 minus 1. So, well, either this is non-zero, and then I get this either this is non-zero, then I get my constant term here. Or if this is 0, it's because I had to stop before. Because here you see that this is 0 precisely when the initial function coincides with the diagonal. R1 is equal to 1. So here you have two derivation division steps, and that means that by simple application of Rolle's theorem, we have that FD of 2 is more than equal to 2. Right? So the problem with this procedure, this is why I get such a huge bound, that when you try to apply it to more, let's say, folded boards, the problem is that you start to make these computations and then you start to produce a lot of monomials, right? Because this is precisely because you have this inner composition here. You all know the chain rule. When you start to derivate, you're trying to your root can have some sort of very, very low word in this form. And you have to be somehow let's say systematic to see that you reduce something, and at the end you are able to sort of generalize this kind of derivation division algorithm and end up with something which is limited. So I forgot to say, of course, here for this bound can be realized by very simple drawing here. And in all these cases, you have an explicit wage. You have an explicit example where this numbers are analyzed. As far as I know, there's one Torregrossa which is quite interesting now in trying to see if this number is untamed. But it's not. It's quite difficult because it's, as I said, it's very far from an algebraic problem. So let's say the usual technique with properties. This is not very useful here. But his idea is to let's say to find things, to look for things which are near the center situation. What's the center situation? So what's the center situation? The situation that you have, there is some parameters A and R, such that. So we say that f of A of R is equal to that, right? So let's try to just to answer this question. What are the inside the space, the two-dimensional space of parameters A and R? What's the variety of, let's say, parameters for which you have this equation? Right? So there is, let's say, there is very simple situation where here I have already just one center equation, but suppose that you have something which is, let's say, more complicated, like this, and you want to know under which conditions of A1, A2, R1, and R2 this is the A, right? So of course, there's very simple ways to simplify it. So there's a formal ways to simplify this word. For instance, you can take the case where R1 is equals to 1, right? Sorry. Yeah, take R1 equals to 1, R2 equals to 1, and A2 plus A1 is equals to 0, right? But there is other ways, there's other ways to arrive to X formula. A1 equals to 0, and then R1, R2 times R2 equals to 1, and then A2 equals to 0. So there's formal way to simplify this word, and there's an interesting question which took a long time to solve, is to show that all simplifications, let's say, all the ways to produce the identity here are precisely the conditions which are given by these formal simplifications. This is precisely the question. Say that the group which is generated by the translations powers, so the group that I mentioned before, is isomorphic to the free product of this group. So essentially this says that there is no relation on this group except the ones which are given by this kind of formal simplification. So this, in particular, this gives you precisely, so there's an algebraic subset inside this space here, which is the sentence conditions. Yeah, so as I said to you, this number grows quite spectacularly, so I'm not going to go into too much in the details, but this is a quite nice message. So I mentioned that there is a new, an interesting byproduct of this derivation division algorithm, which is a sort of a compensator type expansion of this map here. Five minutes? 6. Okay, so in fact, this what I'm going to mention here is quite interesting. If you go back to your original problem when you try to compute the bifurcation diagram, let's say instead of just computing the number of lead cycles, we'd like to know how they organize themselves in the bifurcation diagram, the strata of one dimension and cycles and so on. So, so this is precisely a byproduct of this. I'm going to explain very briefly. So, what we get by this derivation division algorithm is that f of A of R is in fact a solution of what we call a totally disconjugated the number of steps of the derivation algorithm. You have to check them. So what's what we call this conjugate operator? Essentially, it's a differential operator. It's given by the following things. So you have some positive functions, m0, m1, m2, so on. And now, each time you divide and then you derive it, right? So this is the division operator. So if I stop it at this last step, I get a constant. But if I further apply derivation, of course, another derivation here, I get 0. So this means that your function is a solution of this differential operator here. But this differential operator for the n has a very particular form, because you know that there is this composition here with m0 and n, which are positive functions, right? So this is essentially functions which are produced from these monomials here. So these monomials here by successively applying chain rule and so on. But there's monomials produced from the original expression of f, but they are all positive, right? So the idea here is that when you have a function which is a solution of this equation, it can be of such kind of nature, it can be expanded in what we call a Chebyshev system. So it's very simple. Because you have a basis of solution which can be very explicitly written. Like this, we take, let's say, G0, let's say 0. Yeah, so you see that this, when you take G0 and apply the first step here, you get 0, right? You divide it then. And then there's G1, it will be the kernel of the second step, it's just like M0 times the integral of M1, where I'm going to take the let's say, G-integrated field from some basis point on the this is like this point. And then, of course, integrate this. So gk, for instance, it will be m0. So in the form of an iterated integral. Of this, right? So this is the base of solutions. They are linearly independent. And in fact, this base of solution here, they have the very nice property is that this is a consequence, of course, of this total disconjugate equation, is that this base here is a Chebyshev system. So essentially it is the following. You have some solution of the operator like the FAR. It can be written as a linear combination of this function here. And if the coefficient of the linear combination is non-zero, it has at most capital N zeros. So it's very analogous to, let's say, a very simple case of Chebyshev system is 1x to the power n. This is what happens when you take m0, m1, and n equals to 1, right? It's a polynomial. So the nice thing is that when you have a Chebyshev system, so let's say you have a solution FAR, which can be written as a linear combination alpha 0 G0 minus alpha n Gn. And there's a very nice result of analysis. It says the following thing. Now you can make a catastrophe theory, right? So we want to understand the bifurcation diagram of a function, which can be written in terms of this basis. And since it's a Chebyshev system, you know that the bifurcation diagram, let's say, if you suppose that this is sorry, let's do it like this, because here, of course, the parameters will enter on these coefficients here. And by the way, this is precisely the Baltin condition, the Baltin idea of the Chebyshev system. And what Pandix said that since you have a check-check system, then this bifurcation diagram is homeomorphic to the bifurcation diagram of the usual catastrophe of a polynomial of degree capital N. So you have all the, let's say, all the things which appear here, stratification and so on, will also appear here. Of course, it's only a homomorphism, so there is no natural properties which are preserved. Topologically, it's the same diagram. And so 1 minute perhaps. Just to give an example of this case, when you take, r equals to 1, n equals to 1, sorry. So remember that when n equals to 1, I made the computation here. You have 2 steps, and you have m0 equals to 1, m1 equals to 1, and you have m2 equals to r to the power r1 minus 2, right? So you produce this basis here. Let's take the basis point as equal to 1. So t0. Sorry. Yeah. So yes. It's 1. G1 equals to x minus 1. And of course, here you have to produce something which is clearly dependent from this 2. But now you are in a phase where you have x to the power r1 minus x, right? So if r1 is equal to 1, it's not dependent on the x. So this is precisely where appears something which is called the compensator here. If you take 2 integrals here, so G2 is the integral of M2. Right? And then this gives you the following. So this is x to the power r1 minus 1. This is the compensator of the Calabi-Sine. For those of you which know this. Thank you very much.
So thank you, Daniel, for this talk. And we have questions or comments.
In your construction, I cannot see the tower, this beacon, why is so big? Can you give some intuition of this?
Yeah. Because you produce a lot of monomials, when essentially because of the chain group, right? When you iterate this word f a of r is produced by composing things, and this behaves very badly under derivation, because each time that you derivate, you produce more monomials. And well, I tried a lot to improve my bound, but I was not able to find an algorithm. Perhaps it's possible to load this very bad bound that I have here. But it's really due to the, let's say, the way that you produce this by derivation. You can give the yield.
Okay, so.
So I got kind of lost in the talk, but since I'm not an expert or something, but always when I see some kind of polynomial equation and those kind of relation, I learned from my friends in the algebraic geometry that it's unusual technique to take the polynomial in the modular arithmetic modulus p for some p prime, and this could get a lot of information. This kind of technique have appeared in your work?
I've not tried to do this. First, there is you can already try to tackle the algebraic case. So the case where all the powers here are rational numbers. So in this case, you have a way to reduce this to a set of algebraic equations by some kind of ramification, and then you end up with a set of trinomial equations where we are really algebraic ones. So in fact, I asked this for a lot of people from algebraic geometry, but they are not able. Of course, from the complex point of view, you don't have bounds, right? Because as Armengol told us, this very simple equation here, and there is no bound, right? The complex setting. So, in fact, I think there's some techniques of real algebraic theorem which are missing. And then there's a question of where R is not a rational number, then they are very far from the algebraic world. And in this case, I don't know if there is any tools outside the Romansky theory.
So, another question?
Thank you, Daniel, for your nice talk. Your bounds are for the zeros of the equation f a r equal to the identity, right? And you said they are realizable in this world, by which I mean there are values of a and r such that this equation holds true. Coming back to the dynamical setting of a polycycle, did you find polycycles which realize these bounds?
Yeah, as I said, so this is part of standard result. If you are able to find parameters A and R for which you have, let's say, K solution, you can produce a polycycle in a polynomial vector field which has the same number of unit cycles.
The degree is...
It grows linearly.
Okay.
Yes.
The number of...
Yeah, so this avoids symmetry because it potentially could give you some nice way to get better lower bounds for the Hilbert number.
This also contemplates the persistent case. The persistent polycycle case. This also contemplates this
Yes,
case.
yes. Even if you don't break the connections here, these parameters play an important role. Right? You can produce many zeros just by perturbing the R, keeping the connections.
Thank you.
So, we are running out of time, so let's thank the speaker again. That's them.
Okay, everyone, so we are approaching to the end of our workshop. I'd like to thank you all the speakers, all the people presenting posters. Just to say a few numbers, this event, we had 14 plenary talks, 10 small talks, 7 communications of young researchers, and more than 120 participants. Okay, so I think that it was a great success, and it could be indifferent because we are celebrating the 80th birthday of Marco Antônio Teixeira, so it could be different. So I asked for the institutes interested in hosting the next workshop to apply. Okay, so we have received a bunch of applications. So to be completely transparent, I will show all of them here. Okay, so it was difficult to decide, but we had a committee. So this was our list. Okay, and okay, one of them was UNESCO, and the other also. So, the 14th workshop on the dynamical system will take place at UNESCO Presidente Prudente. Okay, so let's go ahead for that. As one of the organizers, I wish you luck. And also, I have to special thanks to my students, Lucas, Luis, Leticia, Luana, or what's the other name? Lucian. And Eduarda, who helped us a lot during these days, okay? And all the other people from our organizing committee. And I hope to see you all soon next year at Unesp Presidente Prudente. So thank you very much and see you next year. That's it.